Anyway, we'll discuss later. Yeah. Does this sound good? Okay. No, okay, we should get started. Let's close the door. Okay, I'll leave you. Okay, let's get started, shall we? It's a smaller class today. Some event going on that I don't know of. It's in the middle of the semester. Yeah. Okay, today we're going to cover an exciting, yet another exciting topic, which is prefetching, which I think is going to become even more important going into the future due to the importance of memory problem increasing. Probably we're going to cover some of prefetching today and some of prefetching tomorrow, and I intend to cover simulation as well tomorrow because that's such an important lecture. Because a lot of what we do for future architectures is simulation. Because we cannot build hardware for everything. And we cannot even have hardware for things that we can imagine. So it's important to do simulation for future architectures. And you've been reading a lot of papers that have dealt with simulation. You're going to see some more today when we talk about prefetching. A lot of the ideas don't get implemented right away. It's very difficult to have a big idea and have the platform to test it. That's why a lot of big ideas get developed by people imagining things and modeling them in some way that may not be perfectly realistic, but that's okay. If the idea is big enough, then you can actually model it, see its effects, and maybe 10 years, 20 years down the road, people will implement it. And some of the things that we're going to discuss here is going to be like that in prefetching. Okay, so let's get started. I had to put that. So we have a busy agenda, meaning we have a lot of things to cover in prefetching. We're going to talk about the many questions in prefetching. What is prefetching? And then 4 questions in prefetching. And then we're going to talk about basic prefetching schemes, software, hardware, execution-based. Execution-based usually is software, hardware, cooperative, but there could be software, hardware, cooperative as well. We're going to talk about metrics to evaluate a prefetcher with, and then throttling, and then talk about advanced prefetchers. I don't know if we'll get to it today, but we'll definitely get to it tomorrow. Talk about reinforcement learning, for example, and run-ahead execution, which is my own PhD thesis. And we're going to also talk about issues in multi-core and multi-threaded systems. Probably some of that today, but let's see. Does that sound good? Okay, maybe, so. Okay, so why are we prefetching? Essentially, we have a memory latency problem, as you have seen in earlier lectures, right? And you have seen this picture that I showed you, where capacity and bandwidth have improved significantly, but latency has not improved as much in memory. And we've discussed the reasons for this. I'm not going to go back to this again. Clearly, part of it is the design choice, industry choice, and historical choices. Part of it is really, it's difficult. It's fundamentally more difficult to improve latency. So this is a fundamental problem in the end. That's one of the good things to focus on in research. If I have to pick some research problem, I would pick the difficult problem because that's where you can have a lot of impact. Easy problem, maybe a lot of people can work on it anyway. Okay, so you've also seen this picture. Memory capacity, DRAM capacity, chip capacity has improved greatly, as you can see, over 54 years or so, whereas latency has reduced not so greatly, even less than an order of magnitude. And if you look at recent years, it has not been improving. In fact, it's been increasing in some areas. But we've also seen that memory latency is critical for performance. These are to jog your memory for many applications. And we've also seen more relatively recent studies that look at new DRAM types, different DRAM types, and how they actually increase latency and how that affects the performance of some workloads. Performance of some workloads actually reduce when you go from an old DRAM type to a new DRAM type because latency increases. Some other characteristics become better, like throughput, bandwidth. But if your workload is not able to exploit that throughput, which may require significant rewriting of the workload, then your workload performance decreases. So this is not good news, clearly, right? Ideally, you would like, with better memories, your performance to get better. with better hardware, any type of hardware, your performance to get better. If that's going the other way around, then you have a big problem. Okay, so people have recognized latency as a problem clearly, and they've developed many techniques. So we're going to cover some of these techniques in this lecture. I'm going to refer you to some other lectures for some of the other techniques. In fact, we've covered some techniques in digital design and computer architecture, caching, for example. That's a very common technique. But I'm going to classify them more, let's say, a little bit more or less rigorously into latency reduction, latency hiding, and latency tolerance techniques. So let's take a look at what these mean. So I think we've seen three things. Essentially, the first technique, the first set of techniques fundamentally reduce latency as much as possible at the source. And we have seen that when we talked about memory latency. Right? I would call this a more data-centric or memory-centric approach. I have a latency source. I want to cut down that latency as much as possible so that I can access data quickly. Fundamentally, this is more data-centric in a sense, right? Because you want to reduce the access latency of that data. And we've seen a lot of techniques to do that in the memory latency lecture. There are more, and you can read about them. Maybe you've been reading about them in the papers, homeworks, etc. The other two approaches are more processor-centric, and today we're going to be processor-centric. But this doesn't mean that these two other approaches cannot be employed, for example, in a processing in memory system. You can have a processing in memory system that can also try to hide latency even more, right? Because maybe you cannot fundamentally reduce latency as much as possible, or as much as required to get even higher performance. Okay, the second approach hides the latency seen by the processor. Fundamentally, by definition, this is processor-centric, as you can see, right? The processor needs to access the data, and you hide the latency as much as possible. And caching is one example. You cache data so that you don't need to access the same data element again and again and again. This reduces latency from the processor's perspective, right? But it doesn't reduce the fundamental latency to bring the data into the cache to begin with. That's the difference between the first approach and the second approach. They can be employed together, of course, but that's a different thing. Prefetching also hides the latency seen by the processor, and we're going to focus on that today. But there's a third approach, which is tolerating the latency seen by the processor. I think this is fundamentally different from both of the other approaches. And the idea here is to overlap the latency, meaning amortize the cost of the latency. Again, this is another processor-centric approach. The processor is accessing some data. It has some latency. You couldn't hide the latency. You couldn't cache it. You couldn't prefetch it. You didn't reduce latency fundamentally as much as possible. Or maybe you did. Still, there's a lot of latency. How do you hide that latency? One way of hiding that latency is to actually do other things in parallel so that none of those become the bottleneck. Altogether, you can parallelize everything. I actually had my favorite example when I was coming to lecture today. Because I didn't have enough time, I didn't have lunch. So one way of actually having lunch, which is a pair, was to actually serialize, meaning have the latency, sit in my office, eat my lunch, and then come here. But then I wouldn't make it in time. So what I did was I was eating my lunch while walking. That's a perfect example of tolerating the latency of eating lunch, right? This way, I really hit the latency of that lunch with doing something else. So that's an example. And we do this all the time, right? Otherwise, everything would be extremely serial. And processors do it as well by trying to parallelize things as much as possible. Right? Multi-threading is one example. While you're accessing one data in one thread, another thread can be executing and accessing some other data element. Another thread could be executing. So you may have thousands of threads executing to access different data elements. And all of those latencies could be overlapped, such that you kind of see only one latency for each thread, right? One access latency for each thread. Out-of-order execution, which you have seen in digital design and computer architecture, is another example. And we're going to talk about run-ahead execution, which is actually a special type of prefetching mechanism that kind of tolerates the latency seen by the processor. But it's an interesting one because it kind of combines both of these approaches. Does that sound good? Okay. So you've seen this slide before. This is a slide from my own PhD thesis proposal, actually, because I was working on memory latency in my PhD thesis. And clearly, these techniques have been employed in many systems. I'm not going to go through this in detail, but caching is very widely used. We've seen examples of it. Unfortunately, it doesn't work always, and it doesn't work for random access patterns, for example. Right? If you have a purely random access pattern, your caches are essentially useless because you're not really, you don't have, in a purely random access pattern, you don't have temporal locality. And you likely don't have spatial locality as well if it's really random access at a small granularity. We're going to talk about prefetching. We're going to see interesting thoughts over there. But multi-threading is also good to think about. Basically, this works well if there are multiple threads. While you're executing one thread, you execute some other thread to hide the latency. This works well for parallel performance in general. But if you cannot parallelize your program very well, if it's serial, for example, if what you have is only a single thread for some reason, as we will see in the later parts of the lecture, we'll see those reasons why you have a single thread. There's a serial bottleneck in many of the programs. With that single thread, it's very hard to parallelize using multi-thread hardware. People have tried this. And when we get to multi-threading, we may actually talk about that. So this is an ongoing research effort that's not easy. And then there's out-of-order execution, which is you execute instructions out of program order, such that while you're waiting for the completion of one instruction that's older, you can actually overlap the latency of that old instruction's completion with some other instructions that are later in the program. Right? That's the core of out-of-order execution. And digital design and computer architecture lectures go into a lot of detail on how to do that. But this requires extensive hardware in the end. But you can also see that a lot of these techniques were developed in the 1960s, which is very interesting, right? These are not the earliest papers, especially caching. There's an earlier paper in 1962. I should really fix the slide. I wasn't fully aware of it when I actually made the slide 20 years ago or 20 plus years ago. But a lot of these techniques are actually very fundamental. And people have improved these techniques. And there's still innovation going on in a lot of these techniques. Okay, so there are lectures on all of these. Today, we're going to focus on prefetching. Okay, so what is prefetching? Essentially, prefetch means that you load the data before it's needed by the program. That's why prefetch, right? Or it's called preloading also. Some people have used the term preloading, but prefetching kind of dominated the terminology, I think. Why essentially memory latency is high? If we can load the data early enough and accurately enough, then we can reduce or eliminate that latency from the perspective of the processor. Again, keep this in mind. That processor could be a current processor or a near memory processor. It could be the processor next to each DRAM bank, for example, in a processing in memory engine. So this idea is applicable across many different paradigms. The upside of this is it can eliminate compulsory cache misses. So what is a compulsory cache miss? Cache miss is basically something that you have not seen before. You access some data for the first time. You've never seen that address generated by this program, but you can predict it. Does that make sense? Caching usually works by you see an address once, you bring it into the cache, and then if you access it again, hopefully it's in the cache, right? It may not be in the cache if it's evicted by some other data, but if you've seen this address once before, and if it's evicted by someone else, it must be evicted because you don't have enough cache space or you didn't manage your cache well. So if you can categorize the cache misses to compulsory cache misses. You've never seen that address before. Capacity cache misses, your cache was not big enough. And conflict cache misses, I think of this as essentially you didn't manage your cache well. Even though you did have capacity, you could have managed it better, and you could have actually kept it in the cache. You have a question? Okay, no. Okay, good. So this is a very, in that sense, it's a very proactive, it could be a very proactive technique, right? You, as a prefetcher, if you think about prefetching, you don't need to have seen the address before. There are some particular types of prefetching that will require seeing the address before in the program. But there are other prefetching techniques that we will see. They will generate the address. They will run programs to actually prefetch for the main program, as we will see. So it could be very powerful. And it's also, it's an area that's really ripe for a lot of creativity and innovation, in my opinion. Okay, so can it eliminate all cache misses? It's good to discover. I already discussed what a capacity miss is, what a conflict miss is, right? If you think about caches. There's also some other miss called coherence or communication miss that it really doesn't fall into any of those categories. This happens when you have multiple processors, as we will see in later lectures. If you have multiple processors, one processor is accessing address A, it's cached in this processor, but then another processor wants to write to that location, which means that you need to invalidate. Well, one way of doing it is invalidating the data that's in processor, the first processor's cache, and bring the data to the second processor. Now you've seen that address, you didn't mismanage your cache, and your cache is big enough, but the next time this processor accesses the cache, it will get a cache miss, right? Because somebody else needed that data, and that somebody else was a different processor that shared that data. Does that make sense? This is called a communication miss or coherence miss, and that's the fourth category of misses. And we will see that a lot more when we talk about multiprocessors. Okay, so caching is interesting, as you can see. So in all of this, we're going to assume caching. That's also another thing to think about, right? Why do we assume caching? Caching is good in the sense that it's locality is present in many programs, and that locality is very hard to exploit without caching. So if you get rid of caches, you used to be able to do that in BIOS in the past. Has anyone tried that? Maybe you got, if you got to go to your BIOS and try disable all caches. Does that still exist, Ismail? It doesn't exist? Well, maybe, I don't know. And I'm old enough to see these things in BIOS settings and general purpose computers. But you could do it. You used to be able to do it at least. If you disable those caches, and you would see the effect on performance. That's terrible. You would wait there for minutes and minutes for Windows to boot up, for example. So caching is extremely effective. Even though it may not be efficient, it's still effective because there's a lot of locality in the program. So we're going to assume caching to be existent in these prefetching lectures. Okay, so prefetching clearly involves predicting what address will be referenced or accessed or needed by the program in the future. And this works if the programs have some sort of predictability in their misaddress patterns. This is interesting. What is predictability, right? That's also good to define, maybe. I cannot define it fully because predictability also depends on the technique that you use to predict things, right? But there is some fundamental predictability problem, which is if the accesses are completely random, like entropy is 100% or 1.00, probably you're going to have a very tough time to coming up with a mechanism to prefetch those random addresses. But most programs don't have random accesses. And even if the addresses may kind of look random to you, maybe you can find patterns in that by mining things. So we're going to see some ideas. Some of them are quite creative, I think, to try to figure out the predictability in the misaddress patterns. And I think there's more room for improvement over here. So keep your minds open. I should say something over here. We have covered, for example, in digital design and computer architecture, branch prediction, right? We have a lot of predictions, speculation mechanisms. Speculation means doing something before you know that it's necessary to do it. Prefetching is one example. Right? Branch prediction is another example. Essentially, when you want to push instructions into the pipeline, you get a branch, and you don't know which path the branch will take, taken or not taken, a conditional branch, and you predict it. If you predict one way, and the branch turns out to go the other way, you're wrong. But you fetched the instructions already on the wrong path, and if you don't do something about it, you would execute wrong instructions. So branch prediction is a speculation mechanism that affects correctness immediately if you don't do something about it. If you mispredict a branch, you're on the wrong path and you need to flush the pipeline, for example, invalidate those instructions. But prefetching is nicer or kinder in that sense, kinder towards the designer of the architecture, because if you mispredict an address, hopefully this doesn't affect your correctness, right? Basically, prefetch data that mispredict the address is simply not used. Does that make sense? So it's good to think about prefetching and virtual memory interaction maybe also at this point. Like if you prefetch some data, you prefetch some address, and you get a TLB miss, what do you do? TLB misses are okay because those are also maybe manageable. If you get a page fault, what do you do? And if you actually get an access protection fault, for example, you're not allowed to access some location with the address you generated, what do you do? Since this is purely speculative, you should really not handle, especially the protection exceptions, right? Whether you handle page faults speculatively or non-speculatively is an interesting issue that we're not going to discuss in this lecture. But think about these from now to begin with. So basically, but essentially with a prefetcher, you don't need state recovery if you design it reasonably. So that makes things nicer in the sense that when you design a mechanism, you don't need to worry about its correctness as much. There could be other issues. So prefetching, for example, causes side channels. People may really try to figure out, for example, how long an access would take to an address, and they could try to infer the data that you're accessing based on that I'm not going to talk about right now. That's not a correctness issue. That's more of a privacy issue, right? Okay, so I'm contrasting this to branch misprediction or value misprediction. Okay, let's talk about basics. As I said, I'm going to assume caching. In modern systems, prefetching is done at cache block granularity, meaning you prefetch cache blocks usually. You can prefetch smaller than cache blocks or larger than cache blocks also, but what you bring in general is a cache block. It can reduce the miss rate of a cache or miss latency of a cache or both. It can be done by many parts of the stack. It can be done by the hardware, microarchitecture. It can be done by the compiler, so it could be architecturally visible. It could be done by the programmer, which requires, again, architectural visibility. It could be done by the system, for example, the operating system. And a lot of operating systems actually try to, well, I don't know if they do it still, but there used to be, when I was at Microsoft, there was this feature that you could enable where the operating system would learn what kind of applications you would launch at what times, using machine learning techniques, actually. And it would prefetch the application from the disk to the physical memory before you hopefully start the application. Clearly, this would save some latency, right? So you can prefetch at different levels of the hierarchy. In that case, it makes sense to learn from the system behavior, right? User behavior. So user behavior could affect prefetching accuracy in that case. Okay, so but we're going to talk a lot about hardware prefetching today, but I just gave you that idea to show that this prefetching idea is actually much more general. It really spans all parts of a system and our actions also, as we have kind of seen. Okay, so this is an example. I will not dwell on this as much because this is relatively old. It's one of our old papers. As you can see, it's an interesting paper because it used to be that the memory controller was on the other side of the memory bus of the processor chip, but it got eaten by the processor chip due to very large scale advance in VLSI, clearly. But that's not the point over here. The point is you have a bunch of caches, and in fact, the cache hierarchy is growing. You have memory controller. The question is, where do you do the prefetching? Right? You could do the prefetching in all of those places, actually. In fact, in existing systems, there are prefetches in all of those locations. This is what I meant when we talked about memory-centric computing. I said that cache hierarchy is part of the complexity, but there's also a prefetcher hierarchy. There's also a metadata hierarchy, which is virtual memory. So our memory systems are extremely complex today. This is one example over here. This is a prefetcher that sits in the L2. It observes requests that go into the L2 cache. And then it also sees what misses in the L2 cache. And this particular prefetcher can actually start tracking what addresses are going to be accessed by the processor. And it can start predicting that, oh, processor is actually accessing this region of memory. So I should keep prefetching before the processor accesses things in that region. Right? So it can see, for example, address A+1 missing in the cache, and it can start prefetching A+2, A+3, A+4, A+7, A+5, etc. Okay, so imagine putting prefetchers across all of the hierarchy. That's what it is today. Okay, before we go into examples of how to do prefetching, let's talk about the 4 questions. Yes. That's a good question. You could actually prefetch on a cache hit, yes, because that potentially gives you an indication that you're going toward one direction. Right? Usually what happens in a lot of the hardware prefetchers is you create a tracking entry when you get a cache miss, meaning that, oh, you're probably in a region that you haven't gotten into the cache before. And what you track the accesses that happen in a region, for example, and then if you get a cache hit in that region, that's an indication that you're actually touching that region. So the prefetcher may actually say, okay, I'm going to prefetch ahead. We're going to see a prefetcher like that. It actually is employed in a lot of Intel processors today. Yeah. But these are all design choices. So that's a good question that kind of prefetches what we're going to cover. When do you prefetch? When do you actually start tracking regions, etc.? Okay. So there are mainly 4 questions in prefetching. There are, of course, details in each of them, but I call them what, when, where, and how. And there's nuances in especially where. What addresses to prefetch, basically. This is called the address prediction algorithm also. And it's very interesting, clearly. When, we're going to talk about that. When to initiate a prefetch request. Do you do it early? Do you do it late? Do you do it on time? Can you do it on time? It's good to think about that, right? Clearly, this is also tightly integrated with the algorithm and also what you do in the other questions. These questions are all tightly integrated together, actually, kind of. Where has multiple dimensions. When you prefetch something, where do you prefetch it? Do you put it in caches or in a separate buffer? Where do you place the prefetcher? Which level in the memory hierarchy? And then there are a bunch of other wheres that we will see in more detail. And then how does the prefetcher operate and who operates it? This kind of like more principles, right? Does the software do it? Does the hardware do it? Or do you do an execution or thread-based prefetcher? Or do you have cooperative prefetchers and hardware software cooperative? Or do you have hybrid prefetchers? Today, the answer is probably hybrid and all of the above, because we have a lot of prefetchers. But we're going to look at these in a bit more detail right now. Okay, let's take a look at what. So what is really this is usually called the prefetching algorithm, let's say. It really deals with what addresses to prefetch. This is important because if you generate a lot of addresses that are not going to be used, and if you try to prefetch from them, you waste resources, right? And these resources are precious resources. We're talking about accessing memory potential. Of course, you could do prefetching between L2 cache to L1 cache. Then those resources are less important, probably. Still important. But if you're prefetching, especially from main memory to the L3 cache or to the processor, anywhere in the processor, you're really wasting precious memory bandwidth. Right? You're wasting also a cache or prefetch buffer space. You're wasting energy. You're moving data. So if you generate a wrong address to prefetch, it could be bad for performance. And there are many cases, actually, this has been bad for performance in real instances. And people turn off prefetchers, for example. And this has been the common, I don't want to call it a myth, but it's kind of like a myth. In server systems, people usually say, oh, I don't trust the prefetcher, so I'm going to turn it off. And the main reason for it is they don't want to waste some of the resources. And they may actually think their access patterns and the workload that they're executing in some of these server systems do not match the access patterns that are being predicted by the underlying hardware prefetcher after they actually do some profiling of the hardware. So basically, you need to be careful because you waste resources, and these resource wastage could be, with the wasted resources could be utilized by demand requests or more accurate prefetch requests. So it's good to think about not all prefetch requests are equal, as we will see later on. Some prefetch requests are much more accurate. Some prefetch requests are much less accurate. If you're wasting resources with less accurate prefetch requests, more accurate prefetch requests that could have improved performance will not get the resources. Okay. So accuracy is important, basically. So this is one metric that we measure prefetchers with. It's not the only metric by any means, but essentially prefetch accuracy is defined as the number of prefetchers that are used later by the program divided by the number of prefetchers that are sent by the prefetcher. Ideally, you want 100%. But we will see that there's a trade-off here, meaning if you want 100% accuracy, you become conservative. You prefetch less. But once you start prefetching less, the other metric that is important becomes worse, which is coverage. Coverage is what fraction of the requests, what fraction of the cache misses that you're intending to reduce are actually reduced. Okay, we're going to see that. So, but let me not get ahead of myself. I just want to define accuracy here. So how do we know what to prefetch? Essentially, there are multiple ways of doing it. And this really ties into how do you do the prefetching. You can predict based on past access patterns, right? You, for example, look at all of the addresses that you've seen in the past or recent addresses and predict based on those. This is using the information that was generated in the past. And we're going to see a lot of prefetchers to do this. Or you can use compilers or programmers' knowledge of data structures. For example, you could create a thread to actually do the prefetching, as we will see later on. Yes? Yeah. Mm-hmm. Would it not be better to evaluate how much latency? We're going to talk about that. That's basically the timeliness. That also is not not necessarily. How do you define timeliness? It's really basically reduced latency potentially, right? There are multiple ways of defining timeliness. Yeah. But I understand what you mean. Basically, why do we have just accuracy or coverage or timeliness? Is there a single metric that can encompass all? It's very difficult to do that, I think. Ideally, you would like to have a single metric. I would say that it's close to, we've seen stall time fair memory scheduling, right? And I like that metric clearly. Ideally, you would like to have a single metric saying, I've reduced the stall time by this much, right? It's very difficult to calculate in general, as you have seen with stall time fair memory scheduling, first of all. That's one downside. And if you can calculate it, it may still not be enough to understand what you're improving your prefetching. Right? the prefetcher may be reducing stall time, but then why is it reducing stall time? Maybe it is highly accurate and also it has a high coverage to begin with, right? Yes, you can use other metrics to evaluate prefetcher performance, how much stall time it reduces, but it may not provide as much insight. But that's a very good point. Improve the prefetcher, for example. Yes, exactly. Yeah. Yes, another question. Yeah.
Is that a domain-specific approach?
Mm-hmm.
To, let's say, I'm a programmer.
Mm-hmm.
So I tell the hardware to choose.
Yes.
Are there some of these?
Yes, yes. I mean, there are works in literature, for example, to do prefetching for graph analytics, graph applications. And they actually do what I just said over here. They usually design some hardware that can be configured to exploit programmers or compilers' knowledge of the structure of the graph, for example. But we're going to see some other domain-specific type of approaches also for linked data structures, for example. So yes, I think specialization of prefetcher is an interesting direction. You could also do this for different machine learning models, for example, right? People have been doing that a little bit. Okay. So essentially, prefetching algorithm determines what to prefetch. And this is clearly a first order thing. Okay, it's good that people are thinking and questioning. Keep them coming. Maybe you'll come up with a much better prefetcher. And this is actually important. People actually spend a lot of time designing prefetchers in industry. I work with a lot of these people. I actually still work with some of those people. And they put a lot of effort into getting this right. And it affects performance. This is an area where you can actually see performance gains in single thread systems significantly today. And there's more to do. Just because memory is a huge bottleneck, as we know, right? Okay, so let's take a look at some of these predictable or not predictable access patterns. Again, I won't go through this in detail, but you can see that this access pattern is quite predictable, right? You can easily design something called a streaming prefetcher or stride-based prefetcher, as we will see. This is maybe a little bit harder to predict. You don't do the next address all the time. These are cache block addresses, but you need to identify that the stride is 42 plus 42, as we will see. This may be a little bit harder, but you can probably get a pattern, right? So you get +2, +t, +4, +2, +3, +4, +2, +3, +4. This looks like I don't know, an IQ test or something. Yeah, I hated those things when I was a kid. It's interesting in a sense, but come on, this is more interesting. Now there's an application for the IQ test. Yeah, you can see another thing over here, which looks kind of maybe not predictable, but XYT is repeating, as you can see. If you can somehow predict that, maybe you'll be fine. Or if you can somehow keep that in the cache, if it's possible. And there's another thing over here, which is, so existing prefetchers are actually quite sophisticated, and they can predict some of these repeating patterns, which is actually a good news. So there are hardware prefetchers in processors that can predict some of these patterns. Okay, so we're going to get back to that. Let's talk about the other question, when. When is equally important? Well, actually, I think all of these are quite important in the end, because you may generate an address correctly, but you may generate it too late, right? If you do it too late, then it's useless for you, right? So when do you initiate a prefetch request? If you prefetching too late is bad, as I've kind of alluded to, but let's start with prefetching too early. Prefetching too early could also be bad, because you prefetch the data, bring it into a buffer, but it may get evicted from that buffer cache before the processor actually needs it, generates the address. So that's also not good. Prefetching too late, in the end, you may not hide any of the memory latency, right? Because you generate the address the same cycle the processor actually requested it. That's kind of not useful in reducing latency. Prefetching somewhere in the middle, ideally you would like to prefetch right before you would like to get the data right before the prefetcher needs it, right before the program actually needs it, right? But it's very difficult to time that. As we have seen, memory latency, there's a lot of interference and variability in the memory latency. It's very, very difficult to time exactly when to generate a request. And that's just part of the problem. It's not just about the memory latency, it's also about the program execution timeline, right? You need to deal with the memory latency to bring with the data, and that is a lot of variability. Program execution has a lot of variability also. the program actually may reference a data much earlier than you expect, right? Because it took some other path. If it took this branch and it took this path, it would reference the data maybe 500 cycles later. But if it took this branch and if it took the other path, it could reference the data 10 cycles later. Right? So there's a lot of variability in the program execution. And prefetching kind of sits in the middle. It has to deal with both kinds of variability to get the data or to get the data right in time. So it's usually very difficult to perfectly prefetch on time. Okay, so basically when a data item is prefetched, it affects the timeliness of the prefetcher, as we briefly alluded to earlier. So prefetcher can be made more timely. I'm not going to define timeliness right now. We're going to get back to this. But prefetcher can be made more timely by making it more aggressive, meaning that it can try to stay far ahead of the processor's demand access speed. So this, for example, if it's a hardware prefetcher, the processor, let's say, is accessing address. It's a predictable address, perfectly predictable address pattern, access pattern. You're accessing address A plus 1, A plus 2, A plus 3, A plus 4, A plus 5, A plus 6, A plus 7. You keep going. And you decide that whenever you see A plus 1, A plus 2, you prefetch everything from A plus 3 to A plus 60 so that you can start getting ahead of the access stream. That's what the prefetcher does. You could do it. Now, that's a lot of requests to get ahead. Assume that you got ahead. What if the processor stops accessing after address A plus 10? You actually generated 50 prefetch requests that are useless, right? So improving the timeliness requires making the prefetcher more aggressive, which usually reduces accuracy. Okay. Improving aggressiveness also improves coverage, as we will see later on. So in software, if you're doing software prefetching, what you can do to prefetch early or try to make the prefetcher more timely is to move the prefetch instructions earlier in the code. So you have this function that you want something to prefetch for, and you have some prefetch instruction that you've determined you could actually execute. You don't execute it right before the function. You execute it maybe, let's say, 10 functions earlier, maybe 500 instructions earlier. Of course, now if you do that, you will generate the prefetch request early, hopefully with the right address, assuming you can calculate the right address at that time. But now, again, the processor may never go to that function that you're trying to prefetch for because there might be some branches in the middle that force the processor not to go to that function, right, because of the program path. Okay, we'll see some examples of this in a little bit. Okay, so that was when. Okay, that's when. Now we're going to talk about where. Where has multiple dimensions. Where do you place the prefetch data? In what structure do you place it in? You can place it in a cache. You can place it in a separate prefetch buffer. Most processors today actually place in a cache. This is, I think, kind of the consensus. The main reason is complexity is too high to add another buffer in the memory hierarchy. Our memory hierarchies are so complex that people don't want to add more and more buffers in general. Again, there could be some exceptions. So in cache, if you prefetch or place the prefetch data in cache, this is a simple design, no need for separate buffers. But you can evict useful demand data. You could cause cache pollution, right? But a lot of the caches today are not very well utilized, meaning most of the cache, most of the data, when you look at a cache, and if you snapshot it, most of that data, even demand data, is not going to be used soon because we don't have a very good caching efficiency. So maybe this is okay. But then you may get unlucky. You may actually evict something that's going to be used soon, right? So you need to be careful, essentially. If you put in a separate prefetch buffer, you protect the demand data from prefetches, no cache pollution. So this could remind you something, right? Now we have separate buffers or separate caches, if you will. Either you have dedicated caches or private caches, one cache for demand, one cache for prefetches, or a shared cache. And we've seen this trade-off earlier, sharing resources versus dedicating resources. So whenever you dedicate a resource, you provide more isolation, meaning demand data is protected from prefetches, no cache pollution. But now you have a whole slew of design choices to deal with. More complex memory system time. Where do you place the prefetch buffer? Immediately. Do you have a prefetch buffer for every cache level? Okay, that's not going to be nice, I think, to begin with. When do you access the prefetch buffer? Do you do it in parallel with the cache or in serial with the cache? When do you move the data from the prefetch buffer to the cache? Do you move the data from the prefetch buffer to the cache? These are all choices that you have to deal with. How do you size the prefetch buffer? In fact, in one of our papers, which we were going to talk about in 2007, HPCA, we have looked at sizing the prefetch buffer. And these prefetch buffers can get pretty large if you have a very aggressive prefetch. They become bigger than some of the caches. Is that a good idea? And then there's the other issue, which is how do you keep the prefetch buffer coherent? Today, we have cache coherence when you have multiple processors. And as a result of that, if someone modifies the data that you prefetched into your prefetch buffer, someone meaning some other processor, you need to make sure you don't get the wrong data from your own prefetch buffer, because in the meantime, someone else modified it. So all of these are very hairy issues, as you can see. And this is an example of how complex our memory system designs are today. And for these reasons, most of the time, this choice is preferred. Okay, I already said this over here. Okay, so where has another dimension. You may say, okay, I'm going to prefetch into the cache, and then immediately the question appears, what cache? I have so many caches in the system, right? Do I actually do it into L4, L3, L1, L2? You can pick your choice. Clearly, these have trade-offs, right? For example, L1 caches, as we have seen in digital design and computer architecture, L1 caches are very tightly integrated with the pipeline, right? The design choices are really dictated by the pipeline, whereas L2 caches are decoupled from the pipeline because you don't need to access them as fast. So as a result, L1 caches are actually very small. They don't have very sophisticated management policies. And if you put prefetches in there, you may be actually destroying the locality of the demands easily. That said, maybe you can actually design a very special prefetcher between L2 to L1 so that you can hide that latency, because that latency is still important for the pipeline, and existing processors actually do that, L2 to L1 prefetchers, etc. So do you have separate prefetcher between levels? And I think the answer is yes, in many cases today. That shows that there's a prefetcher. I don't want to call it a hierarchy, but there are a set of prefetchers that are working. And then, okay, this is which level of cache. And then there's, within the cache, you decided, okay, I'm going to prefetch into all caches. Pick one cache. I got a prefetch coming. Where do I place it in the cache? I have a set associative cache, right? Four-way associative. I have a direct map cache, good luck. You still have a choice. You may actually decide to drop the prefetch, for example, right? Or, yeah, you can have choice essentially. But you have a set associative cache. You have multiple ways. Which way do you, with what priority do you insert the prefetch into those ways? Is it equal priority with blocks that you know are already requested by the processor? If it's not equal priority, what is the priority? So there are these questions that basically come up, right? Or do you change the priority based on the accuracy of the prefetch or some other metric of the prefetch, as we will see? That's, I think, reasonable in general. But you can see that design choices actually multiply. So prefetch blocks are not known to be needed in general, unless you have some other information about the accuracy of prefetching, for example. If you have a least recently used based policy to manage set associative caches, a demand block is usually placed into the MRU position, like most recently used position. But this is even, things have changed. So if you actually have a caching lecture or state-of-the-art caching lecture, you would see that the existing caches are actually try to do more intelligent things than just placing everything into the MRU position if it's a demand request. But assume that this is the case. This is pure vanilla traditional LRU policy. When you access a cache block with the program, you place that cache block into the most recently used position, because the theory is that if your program has a cyclic reference pattern, the most recently used position will be evicted last, and hopefully that will remain in the cache so that you will actually maximize your cache hit rate. Right? That's the assumption. But with prefetch blocks, you don't know that information. So where do you place it? So there used to be some processors that used to place all prefetches in the LRU position, in a way, least recently used, lowest priority. You have an 8-way cache. You place the prefetch into the least recently used position. And if another request comes, and if another fill comes to that cache, to that index, to that set in the cache, you evict that prefetch immediately. Now, this may not be a good choice if the prefetch is accurate, for example, right? So this is an interesting question, though, to think about. And I don't think we found the best policies over here yet. Right, Rahul? Maybe Rahul has found it. Okay. Okay, then there's another where, which is where to place the hardware prefetcher in the memory hierarchy. Another way of looking at it is what access patterns does the prefetcher see? This is kind of relates to your question earlier, but it doesn't cover everything over there. Do you examine, for example, L1 hits and misses? Do you examine only L1 misses? Do you examine only L2 misses? Or do you examine a combination of both? Do you examine only memory misses? Like, do you have a prefetcher in the memory controller, for example? It's good to think about that, right? Well, what does this affect? Essentially, this affects how complete of an access pattern you see and what are the bandwidth or throughput requirements of your prefetcher are. If you see a more complete access pattern, meaning all of the misses and hits that the processor generates, which is whatever is coming out of the processor, load, store, you see all of those. You feed all of those to the prefetcher. Now, the prefetcher needs to keep up with it, first of all, but it could also identify patterns better, right? It could have a more accurate and higher coverage prefetching. But now prefetcher needs to examine more requests. It's much more bandwidth intensive. There may need to be more ports into the prefetcher because the processor may be generating, I don't know, 4 addresses per cycle, right? If you have 4 total load and store ports. Okay. But this is actually interesting because maybe you don't want to see a more complete access pattern. Maybe there's some predictability that you want to exploit in outer parts of the cache hierarchy, right? Because if you think about that, if you see a more complete access pattern, maybe you analyze that access pattern and you try to figure out what to prefetch. Okay, but not all of those accesses may be equal, right? Because you may not actually, some of those may hit in the L2 cache, right? And you may not really want to consider those, right? You really want to deal with, for example, specialize the prefetcher to long latency cache misses. Then you may not really want to see a very complete access pattern. This doesn't mean that that complete access pattern may not be useful for your prefetcher. But you really need to essentially balance the trade-off between complexity and potentially perfect prefetching in terms of accuracy and coverage. If you design a prefetcher, you will know what I mean. Okay, so a modern memory hierarchy is kind of like this. I think you've kind of seen this picture before, definitely in DDCA. But here, there are many places you can place the prefetcher, as we discussed. You can place the prefetcher between main memory and also disk. We're not going to cover those. But people have proposed a lot of operating system-based prefetching techniques, as we've kind of alluded to. But essentially, you can have prefetches all over the place. But I should also say that this is becoming more complicated, right? This is kind of the vanilla memory hierarchy, but we're making it more complicated. We're adding different types of memory, DRAM, other types of memory. It could be phase change memory, but it doesn't have to be phase change memory. It could be very, for example, high bandwidth DRAM versus high capacity DRAM, right? That's already happening. How do you prefetch data between those? Do you prefetch data between those? Usually that happens actually. If you design something like that, people try to overlap the communication and computation. While they're doing that, they're actually trying to prefetch things actually. So if you can think about that, overlapping communication and computation could be done via some sort of prefetching. And then it actually, in larger systems, the hierarchy actually extends even more. So you may have seen this picture earlier, but memory hierarchy today is growing because you may have, oh, why is it going fast? You may have a compute node that's local, and you may have local memory over here. And that memory is not enough. To extend that memory, you have some remote memory locations. This could be a memory node, or it could be some other compute node, but in existing systems, usually you have memory nodes versus compute nodes, and memory nodes essentially store a lot of memory, so that if your memory is not enough, local memory is not enough, you go through this low latency network to get the data from the remote memory. Clearly, this enables even higher memory capacity, and modern data-intensive workloads in large data centers make use of this, databases, for example, or graph analytics, increasingly machine learning also. But you can see that now that even though this is a low latency network, and today's networks are actually quite low latency, it's still latency. So there's some physical latency that you cannot avoid, and you need to search for data over here. So there's more latency in the memory controllers over here. Now, if you get a cache miss in the local memory, how do you actually tolerate the latency of the remote memory? So prefetching is applied in those remote memory latencies also, and there are papers related to this. We have some paper that talks about that, for example. Okay. Any questions so far? Otherwise, I'm going to switch to how. Fascinating, huh? Okay, I find this fascinating. even though I worked on this for 25 years almost. And I still think this is fascinating. Yes?
When we
Yeah.
How does actually putting more pressure on the prefetch device put pressure on the
Yes.
how can this help computations? I mean, this really delicate thing. Because we are putting more pressure on something that is really vital.
Well, okay, it's good to think about if you don't have any bandwidth. So you're thinking about a scenario where memory bandwidth is completely 100% utilized, right? Yes. If you're completely memory bandwidth bottlenecked, yes, putting more pressure, like adding more unnecessary requests, is probably not good, right? But usually that's not the case. But then there's another issue over here, which is the ordering of requests, right? By prefetching, actually, you may change the ordering of requests. So the original memory bandwidth bottleneck may not be in an order that's kind of nice for the processor, right? Whereas if you actually prefetch nicely, that order may be much better. Does that make sense? Okay. But I agree that there are interesting issues over here that has not been examined as much, especially on the memory system side, because we have very complicated memory systems. Usually when people develop prefetching techniques, they don't consider these, I don't want to call it second order effects because they could be first order effects today, like row buffer hit rates, right? If your prefetching algorithm is not friendly to get your row buffer locality to be higher, then your memory bandwidth pressure will increase, for example. But if you have a prefetching algorithm that's actually nicely exploiting open row buffers, then you can actually take advantage of the memory bandwidth capability. So I wouldn't take it as a given that prefetching actually makes memory bandwidth worse. Yes, if you actually send useless requests, it actually makes memory bandwidth worse. But if you actually somehow carefully optimize how you schedule your prefetches, you may actually get more out of the row buffer, for example. In the baseline, okay, let me give you a concrete example. In the baseline, you may have requests that conflict in the bank, open different rows in the same bank. You may get a lot of row buffer what should I call row buffer conflicts. With a prefetcher, what might happen is you predict that, okay, I opened this row, but I'm going to access this row again later on. So let me do all of those prefetches first before opening the row for the next demand. This could improve your bandwidth efficiency. Does that make sense? So that's a concrete example, I think. But these are issues that need to be carefully, I think, understood. And I don't think there's enough done in this area. Maybe Rahul will tell me that there is enough, but yes. Absolutely, yes. Memory controllers are very important, as we discussed. I agree, yes. It comes back to, but prefetching is all, okay, yeah. I think especially high latency, prefetching of high latency requests are really important to co-design with the memory controller. If you're prefetching between L2 and L1, that's a different issue, of course, right? But those are also low stake prefetches in a sense, those shorter latencies that you're trying to hide. When you're trying to hide high latencies on low bandwidth communication channels, those are higher stake requests, both higher stake in terms of performance and also the costs are also very high, yeah, energy. Yeah. Okay, so let's talk about how now. So I'm going to classify prefetching into three categories: software, hardware, and execution-based. Clearly, software and hardware can be combined also without being execution-based. But let's talk about software first. In software prefetching, ISA provides, instruction set architecture provides some prefetch instructions, and programmer or compiler inserts prefetch instructions. So this requires some effort. This usually works well for regular access patterns. In hardware prefetching, you have specialized hardware that monitors memory accesses, and this hardware memorizes, finds, or learns in some way address strides, patterns, or correlations, and generates prefetch addresses automatically. In execution-based prefetching, this could be both either software or hardware-based actually, or again, cooperative. You generate a thread. This thread is specialized for prefetching, and it's executed to prefetch data for the main program. And I already said the second part. So let's start with software prefetching. So this is an old idea. I actually changed these slides, but I don't know. I think you got the right slides, but I didn't update the right slides because I was dealing with multiple copies. So coherence is a problem, as you can see, right? If you have two copies of the same presentation, if you update one, if you don't update the other, this is what you get. So there are actually multiple papers on this topic. There's one on S plus 1991 by David Callahan, Kennedy, and Porterfield. That's actually also very interesting. So I'll update those slides. Rahul will remind me. So basically, the basic idea over here is a compiler in these papers or programmer places prefetch instructions into appropriate places in code. That's the idea. And hopefully, these prefetch instructions, well, not hopefully, these prefetch instructions prefetch data into caches. And they could be manipulated to be, again, timely or not timely, etc. I'm going to show you some examples. This is an old version of x86. It's probably the same. Is it the same? Anybody programs in x86 today? You have essentially a prefetch instruction. And you can see that there are different versions of it. For example, this one, move data from a memory address closer to a processor using a T0 hint. Now you go and look at what is the T0 hint, and you find that prefetch data into all levels of the cache hierarchy. And then you look at Pentium 3 processor, first or second level cache, Pentium 4 and Intel Xeon processor, second level cache. The specification is violated immediately. It says all levels of the cache hierarchy. What happened to the first level cache and the second one, right? So this basically shows that people don't want to prefetch into first level cache. So software prefetching, this ISA description is written by probably a hardware designer, and hardware design doesn't trust the software, as you can see. So they say basically, no, I'm not going to allow you to prefetch into first level cache. So how do you prefetch into first level cache? I think you need to do this prefetch NTA instruction. But again, if you look at the specification, it's kind of fuzzy, right? It doesn't guarantee anything. There are no guarantees. In fact, none of these may be guaranteed. So that's the nature of speculative instructions. Essentially, you can use this instruction and hope that the processor prefetches data into whatever is, it's kind of promising, but it's not fully promising, as you can see. But if push comes to shove and the hardware designer designs this prefetching instruction, they may say, okay, this is a speculative instruction anyway. I'm not going to do anything. This doesn't happen, of course, but these are instructions that are not necessary from the perspective of execution, right? So they could be dropped. Does that make sense? That's the nature of speculative instructions. And again, if you are designing your hardware, you're trying to push it for the next deadline, you don't have time, you have to drop something. What do you drop? Well, prefetch instruction looks good. I wouldn't drop a load instruction, for example. But I guess Rahul likes dropping some load, so maybe he'll talk about that. To guarantee, as long as you can guarantee that load is droppable, I guess you could drop it. But guaranteeing that load is droppable adds extra complexity also. But with prefetch, you don't need to worry. You're guaranteed that you can drop it. Okay, but this is, jokes aside, this is the truth actually. That's how hardware is designed in general. Especially if you have a complex processor, and if you design one, you would know what I mean. Okay, so let's take a look at some software prefetching. So this actually can work very nicely for regular array-based access patterns. For example, here we have, we're adding two arrays together. While we're adding locations indexed I, we issue prefetches for locations indexed I plus 8. So you kind of prefetch 8 iterations ahead, right? This is an example where you can prefetch 8 iterations ahead. So how do you determine how many iterations ahead do you prefetch? Is that your question, or you have a separate? Okay, let me finish this. Well, you need to figure out what's your memory latency. Are these in the cache? How long does each iteration take? And do some calculation. Say, okay, to overcome, basically to make the prefetch timely and accurate, I prefetch 8 iterations ahead. If I prefetched 4 iterations ahead, I wouldn't essentially hide the memory latency of that request when I get to that iteration. If I prefetch 16 iterations ahead, maybe that would be too early. And maybe my accuracy would reduce also, because at some point, this n will be, you will get out of the loop and you will have prefetched 8 extra things, right? Yes? Mm-hmm. Yeah, that's right, exactly. So basically, I'm assuming these are cache block based. Yes, you're right. Basically, you need to do a separate calculation to make sure that you're hitting the next cache block. Yes, I kind of assume that this is cache block based, but it doesn't need to be. You're right. That's a very good point. Any other thoughts here? So you can see that even with this, you need to do a lot of calculation, right? And this is not even, we're not even talking about executing this program together with other programs. Once you do that, your memory latency becomes completely unpredictable. Well, not completely, but likely very much more unpredictable. And you may optimize your program to be perfect given one application. But then if your memory latency is increased, this prefetch may not be effective. Right? So that's the downside of software prefetching in general. It's very difficult to insert the prefetch instructions at the right place when your memory latencies and cache hierarchy, etc., are unpredictable or hard to predict. Okay, but there are other issues, which is clearly these prefetch instructions are part of your program now, right? Which means that they increase your program size, they increase your code size, they take up processing and execution bandwidth, they take up space in your instruction cache. Think about it. Now you can start getting instruction cache misses. Once you get instruction cache misses, you may need to prefetch instructions. And you may need to be prefetching prefetch instructions for prefetching data cache misses, which is interesting, right? So we're going to talk about instruction prefetching later on, but everything that I said applies to instruction prefetching also, except I'm going to focus more on data prefetching to begin with. I think instruction prefetching is still easier, but there are some interesting things over there. So how early to prefetch? Determining this is difficult, essentially, as I kind of discussed, because prefetch distance. Okay, prefetch distance is how far ahead do you prefetch? In this particular case, which loop iteration do you prefetch for? Is it the next iteration, next? And also, that's prefetch distance. Then there's also called prefetch degree, which is how many prefetches do you generate? For example, you may actually generate I plus 8, I plus 9, I plus 10. Now your distance is at least 8, and your degree is 3 whenever you generate prefetches, right? Okay, but this distance depends on hardware implementation. It depends on the memory latency. It depends on cache size, as you said, cache block size, also time between loop iterations. And you may actually perfectly optimize for one processor, one configuration, but your prefetching may not work well if you run it in another processor, another configuration, or with another application that actually changes all of those. So portability becomes an issue with these software-based prefetches. And if you want to go earlier, if you go too far back, it reduces accuracy because there are branches in between. Now you can see this here, right? If essentially you will waste, in the steady state, you will waste 8 accesses, right? Because you would prefetch 8 ahead over here. Make sense? Because you will always prefetch n plus 1, n plus 2, up to n plus 7, right? Whereas your loop will terminate with n. Okay, in the steady state, of course. If your n is 1, then you're not going to prefetch more than 1. Okay, useless. Okay, and then the other question is, now you need to change your ISA. You need special prefetch instructions in the ISA. People came up with interesting things over here, like PowerPC had this data cache block touch instruction. We saw the x86 prefetch instruction. Alpha was a bit smart. They basically didn't add a prefetch instruction. They used the regular load instruction, but you would load into register 31. So the destination register was register 31. And register 31 is always set to 0 in alpha, because 0 is such a nice value, right? You might want to initialize memory with all zeros, for example. That's one of the reasons why a register is bound to 0. But they took advantage of it, so now you don't need to add a prefetch instruction. Kind of cute tricks, as you can see. Okay. Now the question is, okay, this is regular array-based access pattern. Maybe you did it, but hopefully I've convinced you that this is difficult, even with regular array-based access patterns. What happens if you have pointer-based data structures? Before we go into that, go ahead. Yeah. Yes, that's right. Yeah. Yeah, absolutely. I didn't want to get into that, but exactly, yes. If you're doing software prefetching, and if there's some hardware doing hardware prefetching, you may be redundant, and your hardware prefetcher may already be capturing all of these much better than software. And that's going to be my argument, actually. In general, hardware prefetchers can be customized for the particular processor implementation. It doesn't require code to change. And as a result, you can make it work more easily. And on top of that, if you're doing software prefetching, you may actually be reducing your performance if you didn't do prefetching. That's a very good point. Okay, let's take a look at pointer-based structures. This is, I'm doing some pointer chasing, as you can see over here. I'm doing some work on the data pointed to by this pointer. And then I'm fetching the next data structure linked to this data structure. Before I do that, I prefetch the next data structure, right? Okay, not bad, I guess you could do that. But it stops there. Can you do this one? This is a bit difficult because this requires calculation of all of those addresses, right? So you're doing, so pointer chasing always causes problems with prefetching in general. And these are the hardest patterns to prefetch in general. But we're going to talk about that also. But software prefetching, people have developed methods for software prefetching, like using skip lists, etc. I'm not going to go through that, yeah. Exactly. Yeah, it depends on how long the work is over here, right? If this work is a lot, maybe you will get P next early enough. But if this request comes while this request is in flight, you normally merge those requests in the memory system. There are miss buffers that merge the requests or miss status holding registers. Yeah. Okay, but these are just to give you a glimpse of the issues that you see with software prefetching. Clearly, you can imagine other ways of prefetching these structures, but I'm not going to go through that. Okay. Okay, where should a compiler insert prefetches? Becomes a question in software prefetching. Do you prefetch for every load access? This is a bad idea in general, too bandwidth intensive, both memory and execution bandwidth, because not all loads miss in the cache, right? Usually what you do is you profile the code and determines loads that are likely to miss. Now you profiled your code with some input set and you determine that loads X, Y, Z are likely to miss. And I'm going to insert special prefetch instructions or code to actually prefetch them. But maybe your profile input set was not good enough. When someone ran your program, they used a totally different input set and loads A, B, C were the, let's say, worst offenders in terms of causing cache misses. You inserted prefetches for loads X, Y, Z, didn't insert prefetches for load ABC because you thought this profile input set was good. As a result, your performance actually degrades on the real input set that your program runs on. This is the classical compiler profile input set represented in this problem. Whenever you're doing compiler-based approaches or software-based approaches, you need to be cognizant of this, and you need to get some sort of representative input set, which is a very difficult problem in general. Dynamic compilers, if you're actually doing this compilation and insertion of the prefetches in a runtime system, for example, in Java or some common language runtime, where you can actually recompile your code, they may be better because they actually work with input sets, but the input set may change also over time. So this becomes an issue in general. Okay, so basically, how far ahead before the miss, assuming that you decided some loads miss, then the question still remains, how far ahead before the miss should the prefetch be inserted? Now, again, you profile and determine the probability of use for various prefetch distances from the miss. Now, your profile may not be representative for which misses will happen. Assume that that's solved somehow magically. Even then, you need to figure out where to insert the prefetch in the program. Right? And this is a difficult task because there are many different paths that could lead to the same miss or some miss. Again, if you profile, your profile input set may not be representative. So you insert it early and you don't hide the latency. You insert it too far, you actually may lose accuracy as well as time, not timeless, but you may actually, essentially your prefetch data may get evicted before you actually use it. So usually, in general, because memory latencies are so high, you need to insert a prefetch far in advance to cover hundreds of cycles of main memory latency. And this makes software prefetching very hard to do, at least in the general case. With array access patterns, you could actually try to come up with a loop, for example, that does prefetching first and then do the computation. So you decouple computation and communication and somehow get away with it, but in the general case, this is not easy. Okay, that's why we focus a lot on hardware prefetching. This is not to say that software prefetching may not be useful in constrained situations. For example, if you have a machine learning accelerator, and you know that that's the only thing you're running in this thing, and you know the access patterns of different layers and how they communicate with each other, you could actually insert these prefetches nicely. But that's a constrained scenario, right? It doesn't generalize to many workloads. For every workload, you need to do that potentially, right? But then we don't have accelerators for any workload. Okay, how much time do we have? Okay, this is a good time to probably take a break. Let's take a break for 15 minutes. Let's be back at 14:40, and then we will start with hardware prefetching then. Oh, okay. Still coming. All right. Please close the door. Okay, let's continue. Now we're done with software prefetching, at least the portion in this lecture. We're going to jump into hardware prefetching, which is actually could be much more specialized. And the idea over here is that you design specialized hardware that observes load store or cache miss hit access patterns and prefetches data based on past access behavior. That's the general idea. Let's take a look at the trade-offs in this general idea. Because you have specialized hardware, this can be tuned to the implementation of the processor, memory hierarchy, memory controller. You can take that all into account, assuming it's possible. But that's the big advantage over here, whereas you don't have that information at the software level, right? And also, it doesn't waste instruction execution bandwidth, which is a big thing. You don't generate instructions and inject them. You generate memory requests and inject them into the memory hierarchy with specialized hardware. But of course, now you have more hardware complexity to detect patterns. In some cases, software can be more efficient because in software, you know the address patterns, right? But maybe not in all cases also. Okay, so let's take a look at some examples of hardware prefetchers. And the simplest form is really next line prefetchers. This was initially employed in IBM 36091 in 1960s for their instruction prefetching engine. The idea is you always prefetch the next cache line in the generalized form, next and cache lines, after a demand access or a demand miss. This is also called the next sequential prefetcher. And this kind of makes sense if you're sequentially going through some memory region, right? And this kind of works with code, for example. If you have instructions, normally you have a sequence of instructions that you execute, and the instructions are consecutive in memory locations, memory addresses, and the memory addresses are increasing normally, right? Unless you go to a branch. And then you may actually branch out of some part of the code, and then that sequentiality is broken at that point. But this is the exact reason why the sequential processing paradigm is the exact reason why this was first employed in prefetching instructions, because instructions are sequential. Right? But data could be sequential also, right? If you're going through some array, again, you're accessing array indices in a sequential order, and that sequentiality leads to prefetching the next line or next n lines. Okay, so let's look at some trade-offs. I could give more examples, but hopefully this is easy to understand. It's very simple to implement. No need for any pattern detection in this case, right? You see address A, you get address A plus 1, A plus 2, A plus 3, A plus 4. You see address B, you do the same thing. B plus 1, B plus 2, B plus 3, B plus 4. Right? That's the next line prefetcher. We've already discussed this. It works well for sequential or streaming access patterns. Sequential is sometimes called streaming, although streaming has been overloaded more recently. The downside is it can be wasteful with irregular access patterns, right? So if you're not sequential, if you're never accessing the next cache line in the worst case, this doesn't benefit you at all. It hurts you, actually, right? Okay. And even with regular access patterns, I already said that, right? For example, what is the prefetch accuracy if your access stride is 2 and your n is 1? This means that you're accessing address A plus 2, A plus 4, A plus 6, A plus 8, and your n is 1. You're always prefetching 1 ahead A+1, A+3, A+5. So you're always prefetching the thing that you're not accessing, right? You can always find these worst cases, as you can see, right? So it's not flexible in that sense also. Of course, you could increase n to be 2. Then you would be at least prefetching something useful, but your accuracy now becomes 50% only, because half of the things that you prefetch are not useful if your n is equal to 2 and your stride is equal to 2. So you can have fun with these. In fact, in our homework, and maybe in the exam, you'll have some questions related to the sort of access pattern. And then there's the other question. What if the program is traversing memory from higher to lower addresses? Who said that your addresses should be increasing, right? What about decreasing addresses? Do you also prefetch the previous n cache lines? Just to be sure, whenever you access address A, you prefetch everything from A+1 to A+n, and then A-1 to A-n. That's going to be not so good, right? So usually next line prefetchers, at least in unoptimized form, are not that good. What people do, as we will see later, is there's something called direction prediction, especially in more sophisticated locality-based prefetchers. You can predict the direction that you're accessing. So clearly, if you observe the access patterns of the processor, you can figure out, oh, there's this direction. The addresses are increasing or addresses are decreasing. And you can actually try to predict that, assuming you're going to do something like a more sophisticated next line prefetcher. Make sense? Okay. So a little bit more, I don't want to call it intelligent, a little bit more sophisticated prefetcher is stride prefetcher. If you look at this, this is the strided memory access pattern. Again, we're talking about cache blocks. These could be misses. Essentially, this is the access pattern we have. The distance between consecutive addresses is always n. We call distance between consecutive addresses the stride. Essentially, the stride is n in this case. And this is relatively easy to detect. And the idea in a stride prefetcher is record the stride between consecutive memory accesses. If the stride is stable, use it to predict the next m memory accesses. M could be 1, m could be something else. Right? But this should be easy to predict, assuming this is the only thing that you're seeing and recording. So even the stride prefetcher has immediately raised the question, right? How do you decide, what do you base your stride on? Do you determine the stride on a per instruction basis, or do you determine on a per memory region basis? Here, I didn't say anything about who generates these A plus n, right? For example, A could be generated by one instruction, A plus n could be generated by another instruction, A plus 2n can be generated by another instruction, different loads, right? If you're determining your stride given a single load, you would not capture this pattern because you're trying to find strides, whereas the strides are formed based on different loads accessing memory. So we're going to look at both flavors. So let's take a look at instruction-based stride prefetching. This is originally how it was proposed. You essentially have a load instruction using the program counter or address instruction pointer of that instruction. You store the last address that instruction referenced, and you calculate the last stride comparing to the previous address, and you have some confidence level, meaning that you keep seeing the same stride over and over, right? And then you need to tag it based on the instruction program counter. But basically, each load store instruction can lead to a memory access pattern with a different stride, potentially, and you could distinguish between those load store instructions that way. But the downside of this sort of instruction-based stride prefetching is you can only detect strides caused by each instruction separately. There are also other issues, like timeliness of prefetches can be an issue over here. So for example, you executed this instruction, you figured out the stride, you generated the prefetch. Initiating the prefetch when the load is fetched the next time can be too late, right? Maybe you initiate the prefetch you want to initiate the prefetch much earlier. You're in a tight loop, you're executing this load. This load may be every 5th instruction that you execute. If it's every 5th instruction you execute and these actually go to memory, you're really generating these strided accesses very, very quickly, right? And memory latency maybe 500 cycles. So how do you get ahead? Well, getting ahead is basically, if I go back over here, maybe you start prefetching A plus 50n, right? And then keep doing that. But then we already know what that problem is. If you start prefetching that far ahead, maybe you're prefetching too far ahead and the processor will stop going through that stride at some point, right? Okay. So a potential solution is essentially to look ahead in the instruction stream and guess how far ahead you should prefetch. There are multiple solutions to this. I'm not going to go into the details, but people have proposed actually some complicated solutions like determining the look-ahead PC, program counter, etc. I think there may be simpler solutions, but you can read papers to think about that. The other way of doing stride prefetching is memory region based. Why is based repeated over here? Based. Okay, I want to fix that right now. Oh no, that was a bad idea. Okay, that's better. But that doesn't work because okay, better. More. Okay, much better now. Okay, in this case, you don't keep track of strides based on program counter. You don't distinguish instructions. You just distinguish memory regions. You get a cache block address. You chop some bits. This belongs to this region, let's say, in memory. It could be a page, for example. You're in this memory page, or you're in this consecutive collection of pages. Now, you keep track of the address that you've last seen and the stride you've seen and some confidence. And if you basically keep track of whether you see a stable stride in that region, A plus N, A plus 2N, A plus 3N. And then there could be another region with B plus M, B plus 2M, B plus 3M, etc. Right? So now you're looking at strides on a per region basis. Does that make sense? Could be pages or many pages. This could detect strided memory access patterns that appear due to multiple instructions in this case. As I showed you earlier, right? All of those, essentially, each access could be due to a different instruction over here, which is more general. This actually happens in real programs also. And if you think about it, there's a special case of it where you have stream prefetching or stream buffers. You have a memory region-based stride prefetching where N is 1. I'm going to talk about that because it's a very influential paper that introduced the idea. In the end, you could do both, right? Because sometimes it's easier to detect strides based on program counters. There are some load instructions that are actually quite strided. And then there are some memory regions that are also quite strided. You could also combine these two approaches in the end. Make sense? Okay, let me talk about stream or stride-based prefetching trade-offs before we talk about stream prefetching, which is a special case. So special case is essentially you determine N is 1 and you keep streaming. You keep filling buffers called stream buffers, as we will see. So let's talk about trade-offs over here. So you could do instruction-based stride prefetching versus memory region-based. This base is always repeated. I don't know what's going on. It's a copy-paste error. Is this your copy-paste, Rahul, or mine? This is how errors get introduced in the code also. Copy, paste. That's how errors propagate. Okay. So basically, as I said, the latter can exploit strides that occur due to interaction of multiple instructions. And I think the latter can more easily get further ahead of the processor access stream because you don't need to deal with whether you're going to see this instruction next or not. No need for a look at program counter. But the latter is also more hardware intensive because you need to keep track of regions. And how you keep track of regions actually could be a little bit difficult. And the main reason is usually there are a whole lot more regions to monitor than number of instructions, because the instruction working set size is usually much smaller than the data working set size. If you can somehow design a stride prefetcher that hopefully works nicely based on instruction-based strides, your hardware may be less costly. Of course, you can have more coarser grained regions, right? Once you have more coarser grained regions, you can have, for example, large pages, 1 GB regions. Now, the downside is there may not be a single stride in a 1 GB region, right? There may be many strides. As you make your regions coarser grained, maybe you need more strides, and we're going to talk about that also. So this is interesting, basically. Even with a small region, you may actually have multiple strides, as we will see. If you have a 4 KB page, for example, you may be touching different pieces of data structures, and that could actually have multiple strides. So in general, a single stride-based prefetching doesn't work very well. That's I think the consensus in the field. That's why people have developed more complicated prefetchers. Okay, this is the original paper, or one of the original papers on instruction-based stride prefetching. It's going to be on your list of papers to potentially read in the homework. It's a little bit old, but it's a nice one. And these are actually employed in real systems. So there's an instruction pointer-based prefetcher to level 1 data cache, for example, in Intel processors. I don't know if they're still there, but I'm assuming they are. But there are also memory region-based stride prefetching. This is, in this case, stream buffers, which I'm going to briefly talk about. This is a very interesting paper from ISCA 1990, as you can see. And the idea is to prefetch into the data cache. You can see that at that time, there's one data cache. There's no many levels of caching. And you have a stream buffer. In this case, I think you have 8 stream buffers or some number of stream buffers. You see 4 of them, but then a lot of dots. Here, we're going to store the prefetched data into these FIFO queues. Each stream buffer holds one stream of sequentially prefetched cache lines. And on a load miss from the data cache, what we do is we check the head of the queues to see if there's an address that matches. And if there's an address that matches, you take the data from that queue, insert into the cache, and then move the pointer, head of the queue pointer, to the next data element. Clearly, this works nicely if you're streaming through memory, right? Your accesses are to consecutive cache lines. If you're adding, let's say, 8 arrays together, you're streaming through memory, and you really need 8 of those accesses concurrently. And you can get the top of the queue from 8 of those FIFOs. Okay. If you don't have the data, then you allocate a new stream buffer to the new miss address, and then you may have to replace one of the stream buffers that you're not using. The hope is that if you're streaming, essentially the hope is that you're always streaming through memory. If that doesn't work, you may actually have addresses duplicated in different FIFOs clearly. So it's a very specialized way of doing it, but people generalize it later on. You don't have to be this strict as it's proposed in the paper. Essentially, when you have a space in a FIFO, you keep prefetching into that FIFO whenever the address bus is not busy. So you can think of this as a stream-based execution model also. You keep prefetching and filling the streams. And hopefully, the processor would be popping the data out of these queues. Does that make sense? This is a very strict model, but this is the original idea. And clearly, you can criticize this paper saying that this original idea is too strict. Yes, but what's important is the idea. So that's why I think people should be more accepting of ideas as opposed to particular implementations. This is a particular implementation of the general idea of stream-based prefetching, which may not be implemented this way. In fact, it's not implemented in any of the processors that I know of this way. But the stream-based prefetching has influenced a lot of prefetchers going down. So it's good to decouple this idea versus implementation in general when you think about ideas or implementations. Okay, so this is the stream buffer design. It's actually relatively simple. Assuming this is how you process things, you have the cache block and associated address with it. And then you have a valid bit, whether you actually have it in the stream buffer, and then you have a tag. This is kind of like a cache, actually, except it's a queue, right? It's a FIFO queue. When the CPU generates an address, you compare it to the tag, and then see if it's here in the stream buffer. And then there's a prefetch address that's generated. There's always a next address, which is really the address that's missing, that's to be prefetched next into this buffer. Does that make sense? It's a very simple logic, as you can see. And this is from the paper. As you can see, you have multiple stream buffers that look like this. Essentially, the next level after the data cache in this particular design is a prefetcher. And prefetcher prefetches into these relatively strict stream buffers, which is also interesting. Later papers have looked at, for example, whether this is good or whether it's good to have an L2 cache. In some applications where all you're doing is streaming through memory, you don't want to have an L2 cache because these stream buffers are good enough, actually. But they're not general purpose, as you can see. They're very specialized for streaming access patterns. Okay. So there's a more generalized streaming prefetcher in IBM Power 4, which doesn't use specialized stream buffers. Essentially, what this does is this actually shows a picture. You identify memory regions and you prefetch streaming access patterns from those memory regions. For example, you have some data I0, I1. I think these are lines actually, line 0, line 1 in the L1 cache. And you bring, after you use line 0, you bring line 1 over here. After you use line 1, you bring line 5 from the next cache. After you use line 5, you bring maybe multiple lines over here into the L3 cache. And there's a logic to determine this. So it's the same concept, actually. You're streaming, except you're not as, you need to have some metadata to decide what to bring in to each cache, but you don't need to have stream buffers. Essentially, you have this incorporated into the caches. Makes sense, hopefully. You can think about that. You can also read it over here, which says essentially what I just said. And it says 8 such streams per processor are supported. So this is the recommended paper, stream prefetching. It's interesting to look at. It's interesting to look at for another reason, as you can see. So as I said, memory latency has always been a problem in computer architecture design. You can see some old numbers over here. For example, in VAX 11780, which was the fastest processor of its time, you can see the memory time was 1200 nanoseconds, which is pretty large. You can see the cycle time of that processor was 200 nanoseconds. Clearly, memory times have not improved as much as cycle times of the processors. That's one of the reasons for the memory bottleneck. So a missed cost is 6 cycles, and mixed cost is 0.6 instructions because there's a cycle per instruction. And Norm Juppy, when he was designing this prefetchers, was working on Western Research Labs Titan processor, and their projections were more, let's say, worse in terms of missed cost, 12. I think this is actually designed. But then there were projections for having memory latency to be 70 cycles, etc. Today, we're actually easily in the hundreds of cycles. Okay, this also shows that memory latency does not reduce as much, right? So 280 is a projection that's not too far from today's systems. Today's system, general purpose systems, are close to 100 easily, 100 nanoseconds, maybe 120 nanoseconds. And if you actually have even expanded memories, it could easily go to 280 nanoseconds, right? And we're talking about this paper was written in 1990. That's 34 years ago. Is it 34? Yes. Okay. Okay, so any questions? I'm going to generalize the stream-based prefetching a little bit more. So I'm going to call them locality-based prefetching for the lack of a better name. But one of the issues with this sort of stream-based prefetching or stride-based prefetching is they're relatively rigid. You determine your streaming, +1, +1, +1. You determine your striding, +n, +n, +n. Unfortunately, that +n is not easy to determine in general. There are many applications where access patterns are not perfectly strided due to memory allocation patterns and also due to the access patterns. So your memory allocation may not be perfectly aligned with the cache block, for example, or your access pattern, for example, when you're traversing some data structures, you're not always going through the data structures. You're actually traversing the data structure, and then you're looking up something based on some value. And in the next data structure, for example, or an element in the array, you're looking up something else, right? So you may actually be touching different locations in memory that's offset from the base value, which may be A, as we have seen. And some patterns look random to close by addresses, so these may not be easy to capture. So the question is, how do you actually capture such accesses? So I call this locality-based prefetching. This is the paper that describes it, in my opinion, in the best way. I'm not going to go through this in detail in general, but essentially, maybe I should use the board over here. So how do we do that? It's manual. Okay, good. Even better. I don't have to deal with. Okay, but that's not better. So how do we switch the Zoom, I guess? Say it again. Stop sharing is good enough? Okay, let's see. Yeah. Okay. Stop share. Okay. Is that good? No. That's good, right? Or no, I think. Okay, you don't want to see that part, basically. Okay. Complicated mechanism. Okay, now we have another issue, which is how do we write on the board? Hopefully that's easier. Okay, that's fine. We don't need white. Okay. Okay, so look, it looks good, yeah. Something happened. So basically, I'm going to give you the general idea, not a particular implementation. You can actually read the paper for a particular implementation, actually read the patents. They're actually interesting patents. But the basic idea is you get an address, you get a miss, let's say A, and this is determined to be in some region, right? And what you do is you start tracking. So you create a tracker. I'll call this a tracker. So there's some hardware structure now that starts monitoring whether addresses come to A, and you may actually decide A minus 16, let's say, or A plus 16, cache blocks. And then you start to wait for addresses that come to this tracker. And you see that the processor accesses, let's say, address A plus 5, let's say. Now you have some indication that the processor accessed A plus 5 also. Maybe I should do this. And then you can say, oh, maybe the processor is going in the positive direction. You may need more confidence. So wait for another access before starting prefetching. And the processor accesses A plus 1, let's say, at this point. So you got the A plus 1 over here. Now you have another indication that the processor is going in direction plus 1, or the plus direction. So maybe you set the direction to plus, and now you transform that entry so that you don't monitor the negative part. Right. Now I have another issue, which is how do you delete? Just like a Bloom filter. How do you delete elements from a set? I don't want to use my hand, but there must be some solution to this. Is that that's a very heavy-handed solution. So you got to have the right tools for it. I don't want to use this solution either. See, a whiteboard would have been better, I guess, but I like the blackboard actually. So basically, what you do is you stop monitoring to this side. Now you have some confidence that, oh, okay, yeah, let's do it. Why not? You have some confidence that processor is streaming. That's why I call this, I cover this, streaming toward this direction in this region, right? And then now you can start prefetching, right? There are multiple prefetching algorithms over here, but for example, one way of prefetching is maybe you also get rid of that. So you actually expand the region right now because you figured out that the processor is not going down this way. The processor is going down this way. Maybe you expand the region to maximum to A plus 64. I like 64 because 64 times 64 is, can anybody guess what that is? That's interesting math and decimal binary. And that's the page size in general, 4 kilobytes, right? So usually some of these prefetchers try to stay within a page. But now you have a tracker that looks at this region and it knows that, or it thinks that you're going in the positive direction. And you want to kind of get ahead of the processor. One way of doing that is basically saying, oh, I'm going to prefetch up to A plus 8. Maybe prefetches should be different colors. And I'm going to try to get ahead of the processor. So you prefetch A plus 8, you prefetch plus 7, you prefetch plus 6. Oh, I didn't do a good job distancing these things. Plus 4, plus 3, plus 2. You prefetch all of these in between and hope that you're ahead of the processor by 8, right? So now your prefetch stream is hopefully ahead by 8. It could be, you could actually decide to go up to 12, for example. And now you keep tracking, meaning you keep waiting for more evidence that the processor is going the direction that you're prefetching in. And if you get that evidence, you're going to prefetch more. For example, if the processor says, oh, I'm prefetching, I'm accessing A plus 17, maybe you got more evidence, right? So this is plus 17, the processor accessed it. Maybe you prefetch 2 more over here. Make sense? It's not perfect, as you can see, right? It has some directionality and streaming toward this direction. But maybe after that, the processor will access address A plus, I don't know, 6. So you already prefetched it, right? So this is one way. Again, I'm not showing a particular algorithm over here. Usually they're more optimized than what I've shown. You can optimize a lot of these things, but this is the idea of locality-based prefetching. You're really determining a direction the processor is streaming in, or you think the processor is streaming in. And then you're prefetching in that direction. And you're waiting for evidence that the processor keeps streaming in that direction, and you keep prefetching so that you can actually hopefully get ahead of the processor. For example, if you get plus 17 over here, maybe you prefetch even more. Right? That could be one pulse. Clearly, it's very aggressive if you do that, because you prefetched up to a plus 8, and then you saw a plus 17. What do? Maybe you prefetch all of these over here plus some more over here. It would be aggressive because you would generate a lot of prefetches. But if the processor eventually touches a lot of these blocks over here, maybe that's a good idea, right? That's the idea. And variants of this sort of prefetcher are actually employed in a lot of Intel systems, and we talk about that in our paper. Of course, they're much more sophisticated right now. And surprisingly, they're quite effective. I've actually worked on these a lot, and they're quite effective. Of course, if you have a stride, you don't want to do this, right? If you have a nice stride, A plus 5, A plus 10, A plus 15, forget about this. Don't do this, right? Detect that stride and do the striding thing. So you want to filter out things. These are actually for difficult access patterns. And if you actually do this for difficult access patterns, you gain a lot of performance, as I will show you in the next slide. Okay, let's see. Do you need to do something? I'm sharing, but... Okay. Oh, okay. Now I see. Watch out! Don't hit your head or hands. So as you can see, heterogeneity is always comes at extra complexity. So we have heterogeneous modes of presentation, and switching between modes comes at more complexity and more overhead, latency. That's always true. Okay, so this is a description of one of the prefetchers. You can read it, but I'll give you an example. We have actually implemented a lot of these prefetchers in our works. Plus, I worked at Intel actually to look at a lot of the impact. So the performance improvements are actually quite interesting and impressive. They're bandwidth intensive, but reducing bandwidth intensity can be fixed by stride detection and feedback mechanisms. One of the disadvantages of this prefetcher is it's limited to prefetching close by addresses. What about large jumps? Like you're looking at this window, let's say 64, between A and A plus 64, right? What if you jump to A plus 1024, right? That could be in a different page, but usually these prefetchers are not good at detecting it. They think that that's a different region, for example. But it's good to think about those things. But they work actually quite well in real life. This paper from Intel in 2004 shows significant performance improvements with this sort of prefetcher. And I can validate these performance improvements also because I've done a lot of these studies. Okay. So I wanted to put that out because this is actually not written in a lot of papers, a lot of academic papers. I don't think, other than some of the papers that we've written and Intel has written, I have not seen this sort of prefetcher, let's say, examined as much in academic papers. They're usually more limited to, let's say, maybe you can think of this as a more chaotic way of designing a prefetcher, right? But yeah, okay. So what about more complex access patterns? Basically, we talked about simple regular patterns. In this case, stride and stream prefetchers work well. If you have complex regular patterns, and maybe you have some somewhat simple irregular patterns where locality-based prefetching works well. But let's take a look at complex regular patterns also. This is also interesting because if you can design a prefetcher for these complex regular patterns nicely, maybe you reduce the need for these locality-based prefetching that you do, because this is bandwidth intensive, as we've discussed. For example, if you actually do have multiple regular strides that look like this, maybe you should just use that information, right? And you can detect that. You can have irregular patterns, linked data structure traversals, indirect array accesses, multiple data structures accessed concurrently, and maybe random accesses. We're going to talk about some of these. Let's talk about multi-stride detection. I'll spend little amount of time on this, but the basic idea is you can see that the pattern is repeated. And you can design hardware to capture this pattern actually. This, the hardware could be an example similar to correlation-based prefetching, which we're going to cover soon. But what you're doing is really you find out that there's a correlation in the addresses. After 7 comes -6. After -6 comes 12. After 12 comes 6. After that comes -5. These are deltas from the previous address. And then you repeat that. So if you actually somehow learn, I don't want to say learn or memorize, or decide based on past experience that 7 is followed by -6, -6 is followed by 12, 12 is followed by 6. Next time you see 7, you can actually guess you're going to get -6, right? And you can actually make this more general. After you see 7, no, not more general, but maybe more accurate. After you see 7 and -6, it gets followed by 12. Right? And then you can correlate these two things. After I see 7 and then -6, the next thing I'm going to see is 12. I can make a table out of this using hashing, etc. You can actually increase the length of the number of things you correlate on. 7, -6, 12, and then after that comes 6. Okay, so hopefully you got the idea. This is complex but predictable set of strides, and people have developed prefetchers for this purpose. The key idea is given a history or signature or pattern of strides, you learn and predict what stride might come next. And I think I already said this. After you see 7, -6, 12, you predict that 6 will come next. After you see -6, 12, 6, you predict that -5 will come next. And again, I'm not going to go through the implementation over here, but there's a particular implementation in this paper, which essentially, after you see a history of strides and you make a prediction, you can use that prediction to predict what your next stride will be. Of course, your confidence may become lower and lower as you keep doing that sort of prediction speculatively, but this may still be actually pretty good to get ahead. And then after some point, you can say, okay, my confidence is too low, I'm going to stop prefetching. Now you can imagine the implementations of this, which we're not going to go into right now. If you go into implementation of all of these prefetchers, it will take a long time. Okay. Any questions? Yes. Mm-hmm. Yeah, path correlation or path confidence. I don't know what they call it. Yeah, I call it delta correlation. Yeah. Mm-hmm. Like 7, -6, 7, -6, 7, -6, like that, or
7, -6, 12, 6, 7, -6, and then this repeats multiple times.
Oh, okay. Then you adapt to the whatever repeats later. Right? You can do that. You keep updating your tables. Or if for example, if you always see the pattern 7, -6, 4, and then 7, -6, 10, and then 7, -6, 4, 7, -6, 10, you can associate two different addresses with 7, -6, right? Yeah. So this is, I think, this is a generalization of Markov prefetching, which I'm going to talk next, generalized to deltas, address deltas, as opposed to pure addresses. Yes?
There's a cost to prefetchers where you can't put anything, you can't put anything, you can't put a huge model there.
Mm-hmm. Yeah. Mm-hmm.
You have a sense of how big these are,
Mm-hmm.
how big they should be.
Mm-hmm.
They're small, they're too small.
They're not too big. They're not too small. Yeah. They're much smaller than caches. Yes. Yeah, because they don't deal with data, right? They really deal with, especially the delta. Deltas are usually small, right? You don't get huge deltas. And you may decide not to track huge deltas also, potentially. So they're actually reasonably small, this sort of prefetcher. But now, of course, if you try to start training a neural network or machine learning model, then that may become expensive, right? That's true. But these are really table-based mechanisms that are not really learning-based yet. But there are works that look at neural network-based prefetching also. We're going to talk about reinforcement learning. And those will become more and more expensive. Yeah. But it's good to think about that, yes. Okay, so let's talk about more irregular access patterns a little bit more. So I'm going to cover some other ideas. I kind of given you the idea of correlation-based prefetching, but I'm going to cover it a little bit more. I'm going to talk about content-directed prefetching, which is actually, I think, a nice idea. It's a creative idea, let's say. And then we're going to talk about more generally covering irregular access patterns, which is pre-computation or execution-based prefetchers. So this is address correlation. So earlier you saw delta correlation, but let's assume that you have the following cache block addresses that you see. I'm not going to read this. What you can construct is essentially after referencing a particular address, say A or E, some addresses are more likely to be referenced next. Just by looking at this, you can construct a graph, a Markov model, or Markov decision graph, if you will, which basically connects what addresses come after what other addresses and assigns probabilities to the transition between different addresses, right? For example, after you see A, if this is what you've seen in the past, with 60% probability, you will likely get B. Right? With 20% probability, you'll likely get A again. You can clearly construct this online or offline. That's how you can do the delta correlation also, right? Forget about the addresses, you do the deltas, right? Okay, so once you construct this, you can actually record the likely next addresses after seeing a given address. For example, you see address A, B, C, D are the possible next ones. You can record all of them, assuming those are B, C, D, right? I just made it up over here. It doesn't have anything to do with the previous one. So next time A is accessed, you can prefetch B, C, D. Clearly, that could be expensive, right? Or you can assign probabilities. Say, oh, with 80% probability, I'm going to access B, so I'm going to prefetch B, not C, D. Or you can say, okay, I have some extra bandwidth on my bus, I'm going to prefetch all of them. I don't have extra bandwidth, I'm not going to prefetch something that's low confidence or where the probability is low. So if you know all of this information, both what follows a given address and a confidence associated with it, you can play a lot of tricks. Clearly, this is very costly, right? Because you're storing large addresses. And if your address set is huge, then you have a problem. What delta correlation does is it reduces that address set to deltas. You may have a huge address set, but you may have a much smaller delta correlation set. Make sense? Okay. Okay. So basically, in this case, A is set to be correlated with BCD. So what you do is you can prefetch up to n next addresses to increase the coverage of prefetching so that you can cover more misses. And you can improve prefetch accuracy by using multiple addresses as key for the next address. So instead of trying to prefetch just based on seeing A, you prefetch based on seeing A and then B after A. Now you're correlating the key AB with the next address that comes with that C, right? Again, you can use probabilities, that's it. So this was proposed in ISCA 1997, so it influenced a lot of things, including the delta correlation-based prefetchers. I'm not sure if they credit this paper as much as they should, but maybe Rahul knows about that. But I think it's essentially the same thing, but the innovation in delta correlation-based prefetchers is really reducing the amount of addresses that are stored. Okay, so it's also called Markov prefetchers. So let's talk about Markov prefetchers as they're originally proposed. The big advantage is it can cover arbitrary access patterns. For example, linked data structures, right? It can cover anything essentially, as long as you've seen it before. So if you're going through a linked list, A, B, C, D, E, F, G, all of those links, all of those addresses of the linked list data structures are actually random. They have no predictable pattern. You go through it once, you record it, you go through it the next time, then all of them can be prefetched. Right? That's the beauty of it. It can also cover streaming access patterns, not so efficiently though. If you're doing A plus 4, A plus 8, A plus 6, A plus 12, A plus 16, if your stride is 4, you can also do that with Markov prefetching, except it's a terrible way of doing it, right? If you have a regular stride, you just do the stride, but here you need to store everything. You need to correlate A with A plus 2, A plus 4, sorry, and then A plus 4 with A plus 8, A plus 8 with A plus 12, A plus 12 with A plus 16. So you have an entry for every one of these things. Now you can see that the hardware requirements grow significantly. Whereas if you did delta correlation, That would actually reduce the hardware requirements, very similar to a stride-based prefetcher, actually. So that's the beauty of delta correlation. Address correlation is expensive, but delta correlation is cheap. That's why delta correlation is implemented. Address correlation is not implemented in existing processors. So this goes back to your question also. So a correlation table needs to be very large for high coverage. And clearly this is a disadvantage. And recording every misaddress and subsequent misaddresses is infeasible. So delta correlation solves part of that. But delta correlation gives up some things, of course, right? So while I'm discussing address correlation, I should also include delta correlation. You need to have correlation patterns that are predictable, right? You cannot really arbitrarily prefetch random patterns. The beauty of address correlation is the pattern is completely random, but if you repeat it again, then you can prefetch everything, right? Does that make sense? There doesn't need to be any correlation between the deltas. So that's address correlation is much stronger in that sense, whereas delta correlation may not be able to capture that. Okay, so you can have low timeliness. Lookup is limited since a prefetch for the next access or miss is initiated right after the previous one. So you can improve the timeliness by prefetching ahead, of course, as we've discussed. And this can consume a lot of memory bandwidth, especially when your model probabilities or correlations are low. Right? For example, if you see address A, you have 10 different addresses you may see next, and all of them have low probability. Okay, but this is still a very interesting idea. I think one other disadvantage I will mention is it cannot reduce compulsory misses. You have to see at least the address correlation again. Delta correlation may reduce it. Address correlation cannot reduce it. You have to see the same addresses over and over. Whereas with deltas, you just need to see the same deltas. Okay, so hopefully that's clear. Any questions? Otherwise, I'm going to move on to some other idea. Okay, let's talk about content-directed prefetching. As I said, we need more creative ideas, and I think this was a creative idea that was developed in late 1990s. And the idea here is to have a specialized prefetcher for pointer values. There are a lot of ideas actually in linked data structures, pointer values, etc. I'm going to pick this one because I think this is actually a very interesting idea. And the idea is very simple. You identify pointers among all values in a fetch cache block and issue prefetch request for them. Sounds good, right? Now, what does that mean? Basically, you're fetching a cache block. You scan the cache block, figure out which addresses are pointers, which parts of the cache block, the data looks like addresses, meaning pointers, and then you issue a prefetch request for them. It sounds interesting. And it was described in this paper. So if you do this, now you get rid of one problem that we've discussed. There is no need to memorize or record past addresses, right? What you do is you just scan the cache block that you're fetching and then prefetch. And then you can also scan the cache block that you prefetched and look for pointers over there. And then prefetch more. And then you can scan the next ones you prefetched. So you can actually have prefetch depth, which much longer, without actually recording anything. This can eliminate compulsory misses. Never seen pointers basically before, even though they may not be predictable deltas, right? Downside is it indiscriminately prefetches all pointers in the cache block. We're going to try to fix that. So if with more information about software data structures, you can reduce this or some hardware profiling. So a key question is how to identify pointer addresses, right? This is actually interesting. One way of identifying pointer addresses is to software say, okay, this is a pointer. And the software can potentially do that with some accuracy, depending on the language you're programming in, right? Or depending on the runtime system. But that's communicating more information between software and hardware. The original paper basically had a nice, cute mechanism. And the basic idea is you look at the cache block and you have an address for the cache block, which is a virtual address. You need to use the virtual address because pointers are in the virtual space, right? And then you look at all address size values, data values inside that cache block, and compare the top bits, most significant bits of the virtual address of the cache block to the most significant bits of address size values. If they match, you say, oh, aha, I found a pointer. Clearly, this is a heuristic, but it's not a bad heuristic because pointers live in the same virtual address space at the higher levels. That's the idea. Okay, I'm going to give you the idea, example over here. So basically, it's called a virtual address predictor. whether what you've seen in your cache block is a virtual address or not. So assume that this is the virtual address of the cache block. You bring it. Nope, something is happening. Yeah, you bring the data. And this is the virtual address of the cache block. You need to store it somewhere. And this is the address. These are address size values. And you compare the top, I don't know, 12 bits of each of these to the top 12 bits over here. It's 12, right? That's good. And only this one matches in this particular case. The other ones assume that they don't match. They don't want. And you issue a prefetch request for that. Make sense? And this turns out to be not a bad heuristic. I've used this heuristic in my other works, in some of my other works. Okay. So this is not bad, but what if you find a lot of pointers over here? What if this pointer is not very useful? Then this could actually be quite intensive in terms of bandwidth. So we did some work to actually provide more information. Essentially, the problem is hardware doesn't have enough information about pointers. Hardware can guess what a pointer is, but it has some difficulty in guessing whether that pointer, prefetching that address that's pointed to by that pointer is actually going to be useful or not. Of course, you could make the hardware more complicated and profile that information and try to build confidence, but it takes a lot of effort. But software does have that information. It can profile to get more information. So the idea in this work is to have the compiler to profile or analyze the code and provide hints as to which pointer addresses are likely useful to prefetch. So you can have a profiling mechanism to do that. And the hardware uses these hints to prefetch only likely useful pointers. So in a cache block, some pointers are marked. The implementation is a little bit different, as you will see. But some pointers are marked to be likely useful. And if you have a content-directed prefetcher, only prefetches cache blocks pointed to that by those pointers. So let me give you some motivation over here. Implementation is in the paper. I'm not going to go through the implementation, but let's take a look at this interesting data structure. This is a cache block. This cache block, you can see that you have some pointers over here. Each pointer points to a linked list of keys, right? This is really a hash table in the end. And hash table has pointers to different buckets in the hash table. Each bucket is a linked list. And a linked list could be very long. And clearly, these are in different cache blocks once you go into that, right? So the structure looks like key and then two data pointers over here, and then a next pointer to the next next element of the linked list. Now that structure looks like this. When you actually traverse, I don't know why the animations are not working. Rahul, you didn't fix the animations last year? It's fine. Don't worry. Rahul gave this lecture when I was on sabbatical last year. So I always had trouble with these animations. But basic idea is, this is what the layout of this cache block would look like, right? So before I go into the basic idea, I should say that which pointers, so you have multiple pointers over here. You have 3 pointers, right? Next pointer, you have a data element, key. You have the next pointer, and you have the data 1 pointer and data 2 pointer. So we have 3 pointers. Assuming they're sequentially laid out, they will look like this. Key, data 1 pointer, data 2 pointer, next. And this is a cache block. And let's say you have two different linked list elements consecutively laid out in the same cache block over here. Now, if you knew this information, you would probably say, I probably don't want to prefetch the data pointers, right? Because only one key will match, depending on the data structure, of course, right? You may have many matches of the same key, but usually the way hash tables work is only one key will match. And if you have a reasonable design, probably your linked list is reasonably long, maybe not terribly long. But regardless, you probably don't want to fetch D1 and D2 for every single node. But you probably want to fetch the next pointer, right? Because the likelihood of going to the next element is much higher than the likelihood of actually getting the data 1 and data 2 pointers, meaning you matching on all of the locations. So that's the idea over here. If you know this information, if you don't know this information, these are all pointers, and the content-directed prefetcher prefetches 6 cache blocks pointed to those pointers. But if you knew this information, you probably direct through the software, the contact rate prefetcher, to actually prefetch only the next one. And you could mark that in the load instruction, because the load instruction that prefetches, not prefetches, the load instruction that fetches the next, yeah, essentially you can mark it based on the load instruction. We have a way of marking it with a bit vector, but I'm not going to go through that again. But you can actually specify which of these addresses are going to be more useful. This is one way of doing it. This is based on the data structure knowledge. The paper is actually more general. You profile the workload, you figure out which pointers are more likely to be used, and then you set your bit vectors that way. But even if you just look at the data structure, yeah, these animations I'm not going to go through. You basically prefetch only the next pointer. That's the idea. So I think this is actually very interesting. There needs to be more of these approaches. Clearly, this complicates the mechanism, but it solves a real problem with content-directed prefetching. Now, I should also say that content-directed prefetchers exist in real systems also. They try to solve this problem with additional hardware in general. They have some downsides and upsides, but people actually use this sort of prefetchers. So if you come up with creative ideas, it may get adopted. In fact, I think there was some recent work that figured out some security side channel issues and these content-directed prefetchers on some phone models. Do you know that recent work? Mm-hmm. Exactly, yes. Well, security breaches maybe. Yeah, some sort of side channel, right? Yeah. Okay. Okay, so it's good to think about this. Maybe we should put that on the slides in next year or later this year, so that we can actually use it next year. Because next year it'll be forgotten, it'll be out of the cache, right? Yes.
Are these prefetchers safe from on the pointers?
Mm-hmm. Yeah. Yeah, I mean that's a valid concern basically. I don't know. I mean these sort of interactions have not been explored as much. Yes, they could actually, but we may talk about we'll actually talk about prefetch throttling. So if you have a good throttler, it could detect that some of the things that you're doing prefetching may not be useful. So it could throttle the application that's generating those prefetches. I think that could be solved indirectly by doing good throttling. But maybe there could be other solutions also. Okay. So hopefully by now you've seen that there's no single prefetcher that covers all the access patterns. So existing systems actually use hybrid prefetchers. They not only use different prefetchers at different levels, which could be customized for the access patterns at different levels, but a single level may have multiple prefetchers as well. So clearly this gives you better prefetch coverage. One prefetcher may be working on easy to predict access patterns. Another prefetcher could be correlation prefetcher. Another prefetcher could be content directed prefetcher. And you put all of them together and hopefully you cover a lot of the access patterns. You can potentially get better timeless this way because you don't need to design a single prefetcher that covers everything, which is monolithic. You design customized prefetchers for different access patterns that you can more easily make timely. But of course, as with heterogeneity, we've seen earlier, heterogeneity of presentation modes, heterogeneity of prefetchers also leads to more complexity. There are many design optimization decisions. It could be more bandwidth intensive. And now prefetchers can also interfere with each other. They will also interfere with, of course, demands, but they start interfering with each other as well. So they could cause contention, pollution. Now you may need to manage access from each prefetcher. But this is actually the state of the art, essentially. You have hybrid prefetchers, and a lot of the ideas that we have discussed, at least better incarnations, better implementations of it are in existing systems. Yet we still have problems. So they don't solve the entire problem. So that's why this area for more exploration. Okay. Should we take a break or should we go for 10 minutes and then stop? What do people think? No break? Okay. Who votes for no break? Okay. Who votes for a break? Who votes for stopping right now? Okay, I see only no breakers. I mean, I won't be offended if you say break or stopping right now. Okay, let's try to cover a little bit more and then we'll continue. But are there any questions before we cover prefetcher performance? This should be relatively easy because we covered a lot of the metrics already. I just want to put them together. Okay, no questions. So let's talk about performance a little bit more. So this slide puts a lot of things together. We discussed accuracy, use prefetches divided by sent prefetches. We discussed coverage, what fraction of all of the misses that you've prefetched. We discussed timeliness, what fraction of the prefetches are on time. What fraction of the used prefetches are on time? Used prefetches are prefetches that are used by, that are demanded by the processor. Timeless can be defined in another way, of course, right? Or coverage even can be defined by another way. You can have a combined metric. Earlier we were discussing you could have stall time reduction due to prefetching, right? That could be another metric. But these three metrics are actually good to identify prefetchers. I like the timeless definition that's not binary. So this timeless definition says whether a prefetch is in the cache at the time you use it or not determines the timeless. So it's binary. But you could actually determine the timeless based on what fraction of the miss you have covered. It's harder to determine, but that could be part of your timeless metric for a given miss, of course. Yes. Mm-hmm. Yeah. You could, but that may not mean much. So to approximate the effect of that, we look at cache pollution, for example. Yeah. So I didn't talk about that yet. So usually you can design a prefetcher that's good at two of these metrics, but you cannot get three. That's a bit unfortunate. This is one of those cases where you have three metrics, but you get only two. You can think about that. Usually improving accuracy means you reduce coverage. Improving timeliness usually goes well with coverage, but not with accuracy. So accuracy is usually on the other side of coverage and timeliness. But there could be other trade-offs also. And then there's other metrics that we should be concerned about, as we have discussed earlier, bandwidth consumption, right? Because this is memory bandwidth consumed with the prefetcher divided by without the prefetcher. And usually it's greater than 1. It could be less than 1 depending on how you account for memory bandwidth, right? Like memory throughput. If your prefetcher is actually nice and exploiting raw buffer locality, maybe you actually schedule requests in a nicer way, as we've discussed earlier. But if you're actually looking at memory requests as opposed to memory bandwidth, then memory requests are usually greater than 1. But not always. So keep that in mind, especially if you're doing multi-threaded programs, for example, and one program is prefetching for another program, then it's actually you can get lower bandwidth consumption sometimes. The good news is you can utilize idle bus bandwidth if it is available. And it's also good to think about some things that people have not thought about as much, right? We're talking about bandwidth consumption. It's a processor perspective, right? But we have seen a lot of ideas in DRAM, right, to improve throughput, for example. For example, subarray level parallelism, right? If you could actually exploit the DRAM substrate, subarray level parallelism, maybe you can actually, for prefetching purposes, maybe you can do a lot of interesting things. I'm just throwing that idea over here so that people think about it. Okay, so that's bandwidth consumption. Clearly not good for energy either. I didn't put energy explicitly over here, but energy is a metric that is affected by essentially all of these. Cache pollution. Cache pollution is the extra demand misses due to prefetch placement in cache. Right? So this is kind of getting at, or kind of directly getting into what you're trying to get into earlier, right? If you if you place the prefetch early in the cache, the likelihood that you'll get an extra demand miss because you did that early is probably higher. This is a bit more difficult to quantify, but it does affect performance. And there's a quantification method that we have in the papers that I'm not going to go into right now. So prefetcher aggressiveness affects all of these metrics. And we've talked about aggressiveness. Aggressiveness depends on the prefetcher type. For most hardware prefetchers, you have a prefetch distance, which we've kind of defined earlier. How far ahead of the demand stream, processor access stream, is this prefetcher? And then we have prefetch degree. How many prefetches do you generate per demand access? I'm going to define these in a nicer way. You have an access stream. You access address X. And then you have a predicted stream, which is the stream that the prefetcher predicted then is prefetching ahead. So you have a prefetch distance. So here you have P-max over here. Now, your prefetch distance can be small. not as ahead of the processor, so you can be a very conservative prefetcher. Your prefetch distance may be middle of the road, or your prefetch distance may be very, very aggressive. Clearly, these have trade-offs in terms of how they affect accuracy, coverage, and timeliness, right? As you are very aggressive, you can improve your coverage at the expense, and timeliness at the expense of accuracy. Okay, so that's the prefetch distance. Prefetch degree is, let's assume that you have some prefetch distance. When the processor is accessing X, you prefetch P. When the processor accesses X plus 1, prefetch degree says how many next things you prefetch. In this particular case, I'm giving you an example of stream-based prefetching, clearly. But you can think about a prefetch degree for content-directed prefetching also, maybe depth. It's called depth in content-directed prefetching papers. Okay, so how do these metrics interact? Essentially, that's very interesting. Very aggressive prefetcher, large prefetch distance, and potentially large prefetch degree, versus very conservative prefetcher, which has small prefetch distance for small prefetch degree. So very aggressive prefetchers are nice because they can be well ahead of the load access stream. It can hide memory access latency better, but they're more speculative. And very conservative prefetchers are essentially exactly the opposite. I'm not going to read this. And they reduce potential for cache pollution and bandwidth contention because they're less aggressive. So essentially, aggressiveness increases coverage and probably provides better timeliness, but it's likely lower accuracy and higher bandwidth and higher pollution. Whereas conservative prefetchers are likely higher accuracy, lower bandwidth, and less polluting, but they may not cover a lot of misses, and they may be not so timely. And whenever you see something like this, you want to think about, I want to get the best of both worlds, right? So just to give you an idea, these are some studies that we have done. So there's a good correlation between accuracy and performance degradation. If your prefetch accuracy is very low, like 10%, you can lose 20% performance. That's a lot of performance loss over here. This doesn't mean that if your accuracy is high, you're going to get high performance, as you can see, right? If your accuracy, here the accuracy is high, like almost 100%, but the performance improvement is, I don't know, 5% maybe. Maybe it's not doing good coverage or good timeliness over there, right? Or maybe the potential is not very high, yes. So there could be, especially if you're, so here we're looking at single core. In single core, probably less likely to see that. But if you go into multi-core, your accuracy may be high, but because you're very aggressive, you may be kicking out a lot of useful blocks, or you may be delaying a lot of useful requests from other cores. So definitely. So if you read the later papers that I'm going to reference, but I'm not going to go into today, clearly, you will see that an accurate prefetcher can actually degrade performance of other applications as well as system performance. But it's less likely to see that probably in single core. You need to really come up with it. It is possible, right? It's possible by because the DRAM system is very complex. You may actually cause some row buffer conflicts that were not there without prefetching, but you don't see that as exacerbated. Okay, but those are very good questions. I think this requires more understanding of interaction between prefetcher and DRAM system, and maybe DRAM microarchitecture, as I mentioned earlier. Okay, so let me give you some things over here. So for example, these are some results from this paper that we wrote a number of years ago. You can see that these bars are instructions per cycle, single core applications. Blue is no prefetching. And then we look at very conservative, middle of the road, and very aggressive prefetching. So in some cases, very aggressive prefetching is very good for some workloads, right? You can see very aggressive prefetching is better than any other prefetcher, including no prefetching. But for some workloads, very aggressive prefetching is very bad. Some of these workloads prefer no prefetching or very conservative prefetching with a locality-based prefetcher, and also a global history-based prefetcher, as we see in the paper. But I'm not going to talk about global history-based prefetching. So if you see something like this, ideally, you would like to get the best of both worlds, right? Even though very aggressive prefetching improves performance on average over here, it really degrades performance significantly on some applications. You don't want to use the same aggressiveness level for all workloads over here. And we're not even talking about multi-core over here yet. And the idea, that's why the idea of feedback-directed prefetcher throttling was developed. The idea is very simple. You dynamically monitor prefetcher performance metrics and throttle the prefetcher aggressiveness up and down based on past performance. That's one way of modulating. The other way of modulating is you can change the location where prefetchers are inserted in the cache based on past performance. So for example, you identify that prefetchers are not that accurate, you make the prefetcher less aggressive. So it's a bit more sophisticated in this paper than that. There are a bunch of thresholds. You identify whether the prefetches are accurate, highly, medium, or low. And then you look at timeless. And then you look at pollution that the prefetches are causing. If you're highly accurate, you're not late, but you're polluting, we decided decreasing the aggressiveness is a good idea. If you're highly accurate but late, we decided increasing the aggressiveness is a good idea so that you become timely, for example. And then you can fill out this table and you can argue with all of the decisions, some of these decisions over here. You can use a machine learning model to derive this table, etc., which we didn't do at the time. We're talking about 2007 here when the paper was published. But if you do this, if you come up with a mechanism to modulate prefetchers, then you can get better performance essentially. So that's what we see over here. Essentially, we've actually curbed the performance gains. So the purple bar over here is feedback-directed prefetching with dynamic aggressiveness and dynamic insertion policy. You can see that on average, it's better than either dynamic insertion, dynamic aggressiveness, and the comparison point is really the single, very aggressive. So on average, we're much better than prior work. But you can see that in cases where very aggressive prefetching doesn't do well, we do much better than very aggressive prefetching, as well as no prefetching. There's a bigger version of this in the paper. So, but there are some cases you can see where the solution is not as good as very aggressive prefetching. So there's room for improvement. But this curbs a lot of the downsides of prefetching. And unfortunately, this doesn't directly apply to multi-core. We're going to talk about that maybe tomorrow. But I should also mention one more thing before we part over here, which is bus bandwidth. Essentially, we also measure memory bus accesses per 1,000 finished instructions. This is called bus per kilo instruction, bus access per kilo instruction. This includes all of the effects of prefetching. This includes the L2 demand misses, as well as pollution-induced misses and prefetches. Ideally, you would like this to be the same as the baseline, right? Or even lower if it's possible. That's a bit tough to make it possible, unless you're doing multi-threading, which we're not doing over here. This is really a measure of bus bandwidth usage. Let's take a look at how different prefetchers do in the measurements that we have done. IPC's instructions per cycle, bus bandwidth, bus access per kilo instruction is also here. Though no prefetching, you can see that IPC is low. As you add conservative, middle of the road, very aggressive prefetching, feedback-directed prefetching, IPC keeps increasing. That's good. So feedback-directed prefetching improves IPC compared to all of them, average. Bus access per kilo instruction keeps increasing, and very aggressive prefetching is not good. So FTP on average gets you similar to middle of the road. So essentially, if you look at the efficiency of FTP, you can do calculations, etc. Its efficiency is quite good. It gives you a lot of performance boost compared to both middle of the road and very conservative prefetching. That's not as much increase in bus accesses. So increasingly, this is going to be important. But one could argue that you still don't want 10.88. You still want lower. Right? And that's one of the goals in prefetching. It's not only about performance. It's also about bandwidth consumption and energy. Okay, that's the paper. This is probably a good place to stop, but I should say that this paper doesn't directly apply. If you take this solution, put it into a multi-core processor, you don't get a lot of benefits, as this work and later works kind of show. The reason is, in multi-core, you have a lot more contention. You may throttle your prefetcher alone. This may actually doesn't impact performance that much. Or you, for example, you may make your prefetcher very aggressive. This hurts performance of other prefetchers. Right? You really need a mechanism for coordinated prefetching across different cores that are sharing resources. And later works actually developed that coordinated mechanisms, which we may talk about tomorrow. Any burning questions? Yes. Mm-hmm. Mm-hmm. Yeah. Never say impossible. But yes, I mean, certainly it's important to consider the hardware overheads. I agree. Some works are, in my opinion, more theoretical in the sense that they try to understand the potential of using machine learning. But yes, they may not be realistic in the current implementation or current hardware. I agree with that. But they may still have value in the sense that they show the potential of what you could get, assuming you could at some point implement it. Okay. Okay, I'll see you tomorrow.